Good morning. Please, everyone, take your seats. Well, first of all, good morning, everyone. Welcome to the it's already the 9th Nigel Priestley Seminar, since it has been renamed as in honor of Professor Nigel Priestley. So there have already been 9 editions since then. It seems like it was yesterday, so it's incredible how years go by. I'm very thrilled to see such a large audience during the first morning session immediately, which is a very nice thing. I think it's clearly a consequence of the high number of candidates we have today. So the first word goes to the candidates. There are 7 candidates, 4 this morning and 3 this morning and 4 in the afternoon, that will be defending their hard work over the past 4 years. This is a PhD that lasted 4 years when they enrolled these 7 candidates. So it's a very important day to them. So thank you to the families and to the friends for being here to support them. The other word goes to the jury. So we have Professors Maria Polese and Paolo Ricci from the University of Naples, and we have Professor Fabrizio Molaioli from the University of Rome, Sapienza, all friends that have been collaborating with us also in other activities. So also themselves made an effort to be here in presence. So thank you very much for being here today. Well, it's going to be a long day, as you've realized by now. So we're a little bit already behind schedule, so let's start. We will start with the first candidate, Pablo Garcia De Quevedo from Mexico. And I will not read all the titles of the presentations. I will let the candidates do that. Pablo, go ahead.
Thank you. Well, good morning, everyone. My name is Pablo Garcia De Quevedo, and I'll talk about my thesis work, which is called Risk Implications of Progressive Damage on Unreinforced Masonry Buildings. In this presentation, we'll talk about what is cumulative damage and why it's important, the motivation of the work. Then a large part of the presentation will deal on how to measure cumulative damage. Then we'll do some fragility analysis and risk analysis, and end up with some practical recommendations for fragility derivation. So to begin, cumulative damage is an important aspect to consider in risk assessment, and this is because earthquakes are not isolated events. They come in sequences with foreshocks, main shocks, and aftershocks, as well as triggered events. And this, of course, can lead to very severe consequences. This is mainly because we're going to have a large number of damaging events, as well as loss of capacity of the structure as the different earthquakes happen. However, the conventional risk approaches neglect these effects. This happens because mainly 2 reasons. On the side of hazard is because of simplifications in which we assume the events to be independent. This means that we decluster the catalog, so we take away the main shock out of the whole sequence and we discard all the other events. And this, of course, leads to an underrepresentation of the number of damaging earthquakes that can impact the structure, as well as reducing the footprint that can be damaged. On the side of fragility, we always assume that the structure is intact, so we keep the same fragility model and we do not incorporate the loss of capacity that can happen. Our focus here is going to be masonry structure. This is because unreinforced masonry buildings are the ones who usually have performed worse in seismic sequences. We saw this in Christchurch, New Zealand, in the sequences here in central Italy, and the ones in Croatia. where there is a disproportionate amount of worsening conditions for masonry buildings compared to other building types such as concrete or steel. It's also, this happens because it's a brittle material, so of course it doesn't have the same ductility capacity that other building types have. And pair that with the fact that it's one of the most widespread building types on seismic active regions, then you have very big consequences. However, some previous studies that try to incorporate damage accumulation into the risk for masonry buildings have had some difficulties. These difficulties mainly come from the fact that it is hard to reliably measure the increase of damage. This is due to mainly the use of overly simplified models, which can be single degree of freedom systems. Can also be because we measure damage using the maximum drift or maximum displacement, and this is not able then to capture an increase of damage if the intensity of the second event is lower, so that the displacement demand is not higher. And also because we assign damage based only on the global behavior of the structure and not just what happens within the building. So to account for this, we can, for instance, use more sophisticated models such as equivalent frame models. This can still run reliably fast, but give us a bit more information about what happens inside the building. We can use better damage metrics that can monotonically increase. This means that they will capture an increase of damage even if the intensity of the events is not higher. And by assigning the damage state based on what happens on the individual members of the structure and not just the overall behavior. So we're going to talk about how to measure the cumulative damage. And for this, what we did was a modified and recalibrated version of the Park-Anang damage index. This damage index considers a displacement term and an energy term. The displacement term is well linked to damage, as we always use displacement. And then the energy term can tell us a bit more about the extra cycles and the extra damage that we're going to observe. This gives us the capacity of measuring cumulative damage even if the intensity of the second, like an aftershock, is lower than the first event, and also has the added benefit that can help for accounting for duration effects. Its long ground motion could be similar to a sequence of events. This damage index was originally derived for reinforced concrete elements, but here we recalibrated and modified it for unreinforced masonry, and for this we used a lot of experimental data and we compiled a database. This database has more than 130 nonlinear cyclic tests. We considered different masonry types, stone and brick masonry, of course different element types, so we had mostly piers but also spandrels. We also had for different failure modes, as masonry can have different failure modes with shear, flexural, or a combination of both. And we had different levels of information on these tests. We have, for all of them, the force displacement curve, but we also had in a few of them also a bit more information about the evolution of cracks, the image data, so photos at different steps of the analysis, and also sensor data. This is what we use to identify the damage states. So here we differentiate damage states first on a local basis, so for the elements only, and we defined 5 damage states differentiated between the element types. So for piers and spandrels we have different definitions, and also in the piers we differentiate by the failure mode, so shear, which is the widespread damage type, and flexural, which has more concentrated damage and less energy release. Then for the calibration, what we did was a 2-stage calibration. The first one was just to get the parameters of the equation. For this we used all the tests, and we just assumed that the damage index has a value of 1 at failure. We calibrated with that these parameters, the parameter of beta, which is originally in the Park-Anang equation. Here we derived a value for masonry of 0.4. And then a new parameter that we added was gamma, which helps control a bit the uncertainty on the energy term and bound it between 0 and 1. which depends on the number of cycles. The other calibration that we did was the damage state calibration, where we used the more detailed test to try to identify or link the actual physical damage that we saw in the test with the numerical values of the damage index. This depended, of course, on the failure mode and the element type, as they have different damage descriptions. But in this we matched a range of values of the damage index to the actual physical damage. So this way we have a map. Then, of course, we are going to deal with the structure, so we move to the global damage state. Here we use the EMS 98 designations, which give us 5 damage states going from negligible or slight damage all the way to the destruction of the structure. And the way in which we move from the damage states of the local elements to the structure was by using this methodology proposed by Katarian and Gioli, in which we consider the damage state of vertical and horizontal elements, so the piers and spandrels. We take the damage state, we combine it to an equation taking into account their size and number, and we come up with a wall level damage state. This wall level is then compared through a set of rules to what are the EMS 98 designations, and this gives us finally the structure damage state based on its components. Now that we decided how to measure, we moved on to the validation part. So we did 2 validations. The first one was experimental, so based on shake table tests. And the second one was a case study, so a real building that was damaged in the central Italy sequence. The experimental one, as I said, is a shake table test that were conducted here in Pavia about 15 years ago. This was a structure that was subjected to incremental levels of intensity, and damage was captured after each of these events all the way until the structure failed. And we also had an equivalent frame model calibrated for this structure, which we used to model the behavior and to compute the damage using the methodology I described. And what we saw is that the damage is well estimated for most of the components between what we saw in the experiment and what the model tells us. And when we move also to the structure-wide damage state, we also got a good match between what was observed and what we predicted. The second validation is a more interesting case. It's a real building that suffered cumulative damage. It's a school in the town of Biso in central Italy, which is shown there in the map. And it was progressively damaged in the sequence of 2016. And it was mainly damaged by the 3 events shown in the map. Out of those, the second event, chronologically, is the one that caused the most damage because it was the most intense one due to the very close proximity to the site. And also this building was monitored as part of the Italian Seismic Observatory of Structures, which means that we had information about the damage after the 3 events. This is a very important piece of information that we don't always have because the time between main shock and aftershock can be very short, so we don't usually know the damage between each event, but here we do. And since it was instrumented, we know the ground motion as well as the response of the building. And again, there was a calibrated model made in Tremur in equivalent frame that we can use to try to model again and estimate the damage. So we did a comparison, 2 comparisons. One was at the element level, so to see what's happening in all the components. So we compared observations with a drift-based assessment that was done by a different research group, and then our damage index-based assessment. Here at the bottom, I'm showing the 3 boxes show the 3 different damaging events, and they show the percentage of the different piers at some levels of damage, and the levels of damage are indicated by the color. If you see, for the observed case, we saw, of course, a large increase for the second event, which was the strongest, but we still see an increase of damage state, especially on the higher damage, so damage state 4 and 5, between the second and last event, even though it had a lower intensity. If we see the drift-based approach, Since the displacement demand did not grow, it did not capture any increase of damage, so it might mean that the structure didn't suffer more damage. But if we see the damage index based approach has more sensitivity, so it does capture an increase on those two higher damage states. If we put all of that together with the component-based approach, what we get is that both the observed and the damage index-based assessment estimate the same level of damage, so going from 2 at the first event, 3 and 4 at the last event. But if we see with the drift component-based, we don't have that sensitivity to see a change of damage between the fourth and the second and third event. And if we just use a global drift, like interstory drift, we see that we do not match also damage very well. There it says damage state 2 because the damage demand was lower, but it couldn't decrease. Now that we saw how to measure the damage, we can move to fragility analysis. So to introduce damage accumulation into risk models, we need to use damage-dependent fragility curves. These damage-dependent fragility curves do not depend only on the intensity this time, but they also depend on the current level of damage of the structure. So we're going to have a different set depending on the damage state. So each damage state is going to have its own set of fragility curves. And of course, we're going to see a decrease of capacity and increase of uncertainty due to the increased damage. In these cases, we're going to use as an intensity measure the average spectral acceleration. And this is because since we are going to see damage in the structure, the fundamental frequency is going to change, and therefore using a fixed period is not going to give us as good results as averages say. We did the fragility analysis for 5 structures. The first one is the Viso building that I described previously. Then we had 2 other buildings from more or less the same time period and the same region of different configurations and number of levels. And then last 2 modernly designed structures also according to the recent Italian normative of design, 1 regular and 1 irregular. So for the fragility derivation, the process that we use is the multiple stripe analysis back-to-back followed by cloud. This ensures that we are consistent with the hazard. So the process here is to first do consistent main shock aftershock record selection. We organize them in pairs and we leave some time between the signals for the structure to stop moving. We do the numerical analysis and damage assessment as per the method I described. And this helps us to classify the damage state after the main shock, which we are going to call the initial damage state, and then at the end of the sequence, which is the final damage state. Then, using that, we do some damage state and intensity relations between the intensity of the event and the damage state that it reaches. And we do that both for the undamaged case and also for the case where we have already some damage accumulation, where we only keep the damage transitions. Then we use this to fit the curves, and I'll describe this better in a few slides. And for example, for the undamaged case, we use some method like maximum likelihood estimation. And for the damage case, we use something like logistic regression, since it's cloud, or feeding a distribution on the damage states. The sequence are selected using the methodology of Papadopoulos et al., which is for main shock consistent aftershock selection. This means that the spectral shape of the aftershock is going to be realistic to what the main shock is it produces it. So in this case, for each intensity level, so for each return period, we select a group of ground motions. We're using the conditional spectrum, and we capture the causative parameters consistent with the hazard, which are the magnitude and distance. We use this to generate a sequence. Here we use the ETAS model to generate the sequence of aftershocks. And with this, we take the magnitude and distance of the generated events. Using that, we can generate a spectrum for each of the aftershocks, and we condition it on the shape of the main shock. And then we select a record that matches this spectrum. So this way we have a pair of ground motions that are consistent. And this results in something like this, where we have fixed intensity values for the main shock, so it's the stripes that we see, and then we have a range of intensities, of possible intensities for the aftershocks. So the fragility results, going back to this figure here, this figure shows us the damage state at the end of the sequence on the vertical axis, and in the horizontal we have the intensity of the aftershock, so the second event, and the color indicates the initial level of damage that the structure is, so it shows us the transition. So for example, if the main shock would put the structure in damage state 3, and then the aftershock processes to damage state 4 with an intensity of 0.6, it will be that yellow dot there. So considering this, what we mainly see is that there is a big loss of capacity, so the more damage that we have, the points start shifting to the left, so towards the lower intensities. And we see this more with the higher levels of damage, and this is reflected also in the fragility curves. So these are the fragility curves for the first building, the Viso building, where we have at the top the intact case, so just main shock, and then we have all the damage-dependent ones below. And what we see is, again, that the median capacity, for example, is shifting to the left because we're losing capacity, and we are also increasing a lot the dispersion. This is most noticeable when going from one damage state to the immediate next. So, for example, there at the bottom, going from damage state 2 to damage state 3, we see a very significant difference in the fragility with respect to the intact case. So to generalize for all the buildings, what we did is that we took the parameters of the damage-dependent fragility curves, and we divided them by the intact case. So the median and the standard deviation divided by those of the intact. And we came up with this plot. This plot shows us the ratio between the parameter, here in this case is the median, of the damaged cases over the intact for reaching the final damage states that are on the horizontal axis, and the color again tells us which is the initial level of damage. Here the dotted lines is just the range for all the different buildings that we considered. And while there is some variation, as we see a range, we do see that most structures follow the same trend. So as you see more damage, the capacity decreases, so we see the points shifting down. And in all of them, what we saw is that the largest change again is when going from one damage state to the immediate next. So for example, the point that's highlighted there tells us from going from damage state 3 to damage state 4, you on average lost half of the capacity. We see for the dispersion, we see something similar but with increases, so it will more or less double. And this happens because, of course, the lower intensity, so we're pushing the range to the left, so we have a bigger range, which increases the uncertainty and moves the median. Now these values, I'll go back to them in a few slides, which they can be used to make simplified damage-dependent fragility curves coming from a non-damaged set. But first I'm going to show some results on the risk assessment. So we did individual risk assessment for the 5 buildings, and we compared 3 cases. The first case is the conventional approach, so main shock only, in which we use just our conventional Poissonian catalog, and we leave the intact fragility curves. The second case is the clustered intact, in which we introduce the sequences in the hazard, but we do not change the fragility curves, we leave them intact. This is to see only the impact of hazard. And finally, the last case is clustered with cumulative damage, in which we are introducing both the increase of hazard with the sequences, and we are also using the damage-dependent fragility curves for these different buildings to see the impact of both. So we compared first in terms of probability of damage, where we already start seeing some significant differences. So here we're showing the annual probability of exceedance of different damage states for 3 of the buildings. And we have the main shock intact in yellow, the green is the clustered intact, and then the red is the clustered with damage accumulation. And we see that there is a big difference in the rate. Here, if we introduce hazard, we see a more or less constant increase in all the damage states from about 50 to 180% compared to just leaving the main shocks. And if we add other damage accumulation, we can take it all the way from 60 to 300%. This happens mostly at the highest levels of damage, so damage state 4 and collapse. Of course, because we are losing more capacity, so we are more likely to collapse the building. In terms of losses, these effects diminish a bit because losses are controlled by the frequent events, so the ones that produce the lower damage states. So we don't see as much, but we still see an increase due to only hazard. In terms of average annual loss, we saw an increase compared to main shock only going from 30 to 60%. And if we added damage accumulation, we got an extra 15 to 25%, so it was still a significant increase. And then we did a regional assessment. So in this regional assessment, we studied the central Italy sequence. So we took the exposure of the impacted area, which is mainly unreinforced masonry buildings. And we also had the information from the surveys that were performed in a few of the towns that were impacted, where we also have information after the first event that was in August, and then at the end of the sequence, so we can see the damage evolution. And we also had the shake maps, which we used to build our hazard model, which was based on ground motion fields. For the fragility, I did what I mentioned previously, in which we took an existing set of fragility curves. So these were empirically based for unreinforced masonries on buildings on that region. And we altered it by the factors that we obtained for the other buildings. And with this, we obtain a simplified set of damage-dependent fragility curves. So there at the top, we have the curves as they are, so intact. And then the rest ones, ideas 1 through 4, are the damage-dependent that we obtain just using these factors. Now, these fragilities look different from the ones I showed previously because, of course, they're empirically based. They are for large classes of buildings, so we have more uncertainty. They're using big ground acceleration. So all of this makes us lose a bit of the accuracy, but it's what we have to do to move to a regional assessment. So we compared, first we compared the damage between the observations, and we also again did a comparison in which we include cumulative damage in the fragility, and then another in which we just use the intact fragility curves. For the town of Amatrice, here we are showing the fraction of buildings at different levels of damage after the first event and at the end of the sequence for these 3 cases. And we saw that there was a good match overall in the estimation of damage, both after the first event and then at the end of the sequence. We saw that adding cumulative damage helped fit a bit better in the collapse case. For other towns, the initial prediction, so the initial estimation with the fragility curves due to the uncertainty was not as close to the observations, but we still see that at least in terms of collapse, if we included the damage accumulation and fragility, we improved the estimation. Of course, the main thing to consider here is going to be the hazard. So if we were only to take the main shock, the strongest event, we would underestimate quite significantly. As you can see there for collapse, the main shock only case is a very, very small fraction of what actually was observed. In terms of losses, we cannot compare to real data because there is no loss data publicly available. So these are not realistic estimates, but we still can make some relative comparisons. So we compared including cumulative damage and leaving the fragility intact. And of course, after the first event, there is no damage accumulation, so we obtain the same estimates if you focus on the total loss value. But the more events, we start seeing the bigger differences. So after the second event, we see more or less a 10% difference by just including damage accumulation. And at the end of the sequence, it's almost 20% difference in the total loss. Again, the largest contribution is going to be hazard. if we were only consider the main shock, so the largest last event, we will obtain only about 40% of the losses of the whole sequence. So with this, what I should highlight is that we should consider both sequences and also damage accumulation to have the full picture. And finally, I'm just going to very briefly talk about other projects I did in my PhD that I don't have much time to introduce that deal with hazard consistent fragility. So the first one was to assess the eligibility of using soil recorded ground motions when we want to do assessment on a rock site or at rock level. And in many cases, we don't have enough ground motions that were recorded at rock, so we are forced to include some soil records. So for this, we just tested extreme cases. We had a group only with soil ground motions, another with only rock ground motions. And what we found is that if we are enforcing hazard consistency through careful record selection, in this case through conditional spectrum, the results are unbiased. So we obtain very similar fragility curves, even if the ground motions are from extremely different sources. And the last one was an optimization procedure. This one is an iterative procedure that uses linear interpolation and Bayesian updating to reduce quite significantly the number of analyses required on multiple stripe analysis. So in this case, we start with a prior set of parameters. So we have a fragility curve that comes from literature or from a very simplified analysis. And the algorithm will automatically identify which are the stripes that that will give us the most information, so which ones to run, and it will quite quickly converge to a benchmark solution. So it will find the best stripes to run and update the fragility curve. We tested this with a lot of building types, damage state definition, and models, and we obtained in all of them a significant reduction of analysis time. So just to conclude, we should account for cumulative damage and sequences in risk modeling. If we use component level analysis and engineering demand parameters sensitive to damage accumulation, we will be better at measuring and capturing these effects. Here the damage index that we calibrated and modified for unreinforced masonry is a good candidate for this type of analysis. What we saw on the validation, both on the real case and in the experimental case, is that we were estimating the damage reliably. Also, this set of reduction factors for the fragility can be also useful for simplified fragility curve derivation. What we saw in the results of risk is that if we neglect damage accumulation and sequences, we are going to underestimate a lot the consequences. When we scaled up to regional level, of course, we increase the complexity, we reduce the accuracy, but we can still enhance the estimates. And finally, that if we are careful with record selection, we can be more free on where the records come from, and that this proposed method of Bayesian updating and linear interpolation can be good for optimizing the analysis time. These are some of the publications that we did during the PhD, and thank you.
Thank you, Pablo, for staying within 30 minutes. So we now start with questions from the evaluation committee. Fabrizio.
Thanks for your presentation, very clear and detailed in each part. I appreciate it. And I would like to ask you some comments and more there, other things, in two things. At the beginning of your presentation, you discussed about the not usefulness of single degree of freedom systems. Have you checked it with in particular with some single degree of freedom recently defined that takes into account cumulative damage in terms of energy? Mm-hmm. And the second, connected to this question, have you checked your very detailed experimental test-based only in terms of energy directly, not including drift?
Yeah, thank you for the question. Yeah, for single degree of freedom systems, they can work as long as we properly account for degradation and so on. And the thing is that they would have to be somewhat calibrated also to the levels of damage if we want to use some metric like the damage index. So calibrate the response of the, say, full structure, which is what the single degree of freedom would try to mimic, and the final damage. So we will need somehow a database to make that link. But yeah, I mean, in theory, that's a step that I wanted to do at some point, to match like a database of final damage with just the global response to try to simplify the assessment. And for the second, we tried, but it's a lot more uncertainty. I think that adding more information through the drift, it helps us at least point to the level of damage, and then just let the energy part try to just tell us what more damage we're getting to the repeated cycles, rather than just energy on its own. I think it would be more complicated to define the size of the cycles or something like that.
Thanks.
Thank you for your presentation. Just one question. Regarding the calibration of the energy parameters in the Park and Dunk formulation, if I understood well, this calibration was dependent also on the failure mode of the panels, right? So you calibrated different values of these parameters depending on the failure mode. I suppose that there should be a significant difference between the values of this parameter depending on the failure mode. Is it correct? I mean, which kind of difference did you find depending on the failure mode?
Yeah, in terms of the ranges, yes, they are quite different. Also, because in some failure modes, there is no, for example, in flexural damage, we skipped one of the damage states because the behavior remains quite similar until heavier levels of damage. So yeah, we had quite different ranges. In terms of the beta, so the weight, we obtained more or less the same value, but in terms of the range, it is different for the failure modes and also for the spandrels.
Thank you for the presentation, very interesting. I also have a question connected to the damage functional, the Park-and-Dunk damage functional, and its potential use to assess the behavior of the building and the accumulation of damage. So we understood it was calibrated based on experimental tests, so in a way, of course, starting from cyclic behavior simulated in the lab. But did you think about even assessing how the model responds to different kind of earthquakes, apart the sequence, but only considering the single earthquake characterized by their cumulative damage potential, so more impulsive earthquake or more earthquakes that have higher cyclic potential, and just to assess how this kind of model allows you to evaluate the different responses of the buildings and if it works satisfactorily?
We did not necessarily check for like pulse-like or different types of earthquakes. The test that we made was we did analysis between long duration and short duration, and in that one we did saw that this damage index was capturing also more damage for the long duration events. So in that regard, yes, we tested that, but not for the type of signals. No, that more or less is accounted in the record selection, but we don't have a systematic way of testing it yet.
Okay, thanks.
Okay. Our doctoral defenses follow a conference format, as you know, so because we still have a couple of minutes, if someone else from the audience wants to ask any question. Yes, Rui.
Well, first of all, I wanted to have the opportunity to congratulate you on the work and in particular in the presentations. That was quite a nice set of slides. Well done. Very, very nice attention to detail, also in color selection. Very well done. Do you mind going back to slide number 29? And yeah, 29, yeah. It's probably something that, since I've never worked on cumulative damage, there you go. It's something probably obvious for those who have worked in the field, but not for me, which is when you look at the blue square in the bottom right plot, that when you go from damage state 2 to damage state 3, the blue square ratio increases, and then it starts decreasing again. You show this plot as well on slide number 24, and I'm sure it's something obvious, but I wonder if you could help me understand why is it that you have that increase there from 2 to 3 and then decreasing from 3 to 4 to 5.
Yeah, thank you. In that case was one particular building, which looks a bit strange that we see like it's gaining capacity, but it's mainly because the shape of the fragility changed significantly. So while the median point moved a bit to the right, since the slope changed, we still see more damage for lower intensities, but the median is a bit shifted to the right. It's just depending on the record that we used and the range of intensities for the damage case.
So you think this would not be something that you would generalize for other masonry structures? Or?
It can be. I mean, if we take the median value, so the ones in the squares, that one is basically at 1. What it means is that for that damage transition, there is barely any loss of capacity, so it doesn't change that much. It's only an adjustment in the slope, but the value, this value is still used for this generation, and we still saw some increases in damage, so it's still functional. Yeah.
Thank you.
Well, actually, you can observe the same trend for buildings 2 and 3, shifted in the damaged states, right? So there's always an initial increase and then a subsequent decrease. Okay, I think we wrap up Pablo's presentation. Thank you again, Pablo. And now we take a long trip from Mexico to Sri Lanka with Maithree and, to the best of my capacities, Kurukulasuriya. The floor is yours. Go ahead.
Thank you, Professor. Bit shorter than Bob. Good morning, everyone. Thank you all for being here today. I'm very pleased to present the research that I conducted in the last 4.5 years, which focused on the seismic behavior of existing unreinforced masonry infills made of horizontally perforated clay units. And it involved an extensive experimental campaign and numerical investigations. And this work was supervised by Professor Guido Magenes and Dr. Paolo Morandi. In the course of this presentation, I will walk you through the motivations and objectives of this research and introduction. I will provide some background on the seismic assessment of masonry infills, introduce the experimental campaign, highlighting key findings, present the numerical investigations and results, and conclude with key takeaways and some recommendations for future work. This study was motivated by the high vulnerability of masonry infills to earthquakes, and as you can see in these examples, collapse of infills can pose a significant threat to life safety and also lead to major economic losses. During earthquakes, infills are subjected to in-plane interstory drifts and out-of-plane accelerations, and in-plane drifts cause most damage to the infills that are in the lower stories, and out-of-plane actions cause damage to the infills in the upper stories due to increasing demand. However, large damage is also observed in the mid-stories due to the interaction of the in-plane and out-of-plane actions. Therefore, infills should be assessed or designed to limit in-plane damage and also to prevent out-of-plane collapse. However, in current code provisions, infills are treated as non-structural elements, and guidelines provided for infills are rather general and inconsistent. Traditional masonry infills are non-engineered elements constructed after hardening of the surrounding frame, and often found in double leaf configurations. There are no special connection or structural gaps provided in the boundaries. A wide variety of infill typologies are used throughout the world, and their seismic behavior is complex due to many interacting parameters involving the infill, the surrounding frame, and also the global structure. There has been a significant amount of research dedicated to understand and improve the infill seismic behavior. However, dynamic out-of-plane behavior has not been explored extensively, especially accounting for in-plane damage. So this study aimed to fill this gap with an experimental campaign conducted at IUSS Center Pavia, which characterized the seismic behavior of an existing infill typology commonly used in Italy in pre-seismic era structures. The in-plane cyclic behavior and out-of-plane dynamic behavior was investigated. First, the tests were conducted individually to ascertain the behavior in each direction, and also sequentially to investigate the influence of in-plane action on out-of-plane behavior. Different boundary conditions were considered in these tests, and also numerical investigations were carried out to simulate the out-of-plane behavior using finite element and distinct element methods. I will first talk a bit about the seismic assessment of masonry infills. The seismic demand and capacity can be assessed in the in-plane and out-of-plane directions, which is parallel and perpendicular directions to the infill panel. The in-plane demand can be assessed from the interstory drift demand of the frame structure and using the diagonal strut model for infills. The in-plane capacity is based on possible shear failure modes, namely diagonal cracking, shear sliding, and corner crushing in the infill, and also failure of frame joints. In the out-of-plane response, the out-of-plane demand of the infills can be evaluated starting from the response of the primary structure to the ground motion, and obtaining the flow motions, and assessing the response of the infill to the flow motions. And out-of-plane force demand is calculated considering the distribution of the accelerations over the panel. The out-of-plane capacity is governed by arching mechanism, which can develop in one way or two ways if sufficiently rigid boundaries are provided. Basically, when the infill moves out of plane, the restraint provided from the boundaries exerts a compressive thrust in the thickness of the infill, which produces a resisting moment, and this resisting moment can be computed as the product of the compressive thrust and the lever arm, and the out-of-plane force capacity can be evaluated from this resisting moment, considering the distribution of forces over the panel. Moving on to the experimental campaign, I will first describe the specimens, materials, test setup, and loading protocol and instrumentations used. A slender, weak infill typology with horizontal perforations was investigated, which comprised of clay units of 12 centimeter thickness, and it was plastered on one side with a thickness of 1 centimeter to represent one leaf from a double leaf configuration. Full-scale infills were built within steel reinforced concrete frame and the infill was connected to the frame with a mortar layer. In-plane pseudostatic cyclic tests and out-of-plane dynamic shaking table tests were performed, both individually and sequentially. Total of 9 specimens were tested in 2 batches. In batch 1, 4 specimens which were fully connected to the surrounding frame was tested, and also 1 specimen had vertical gaps at the column and was connected to the top and bottom to represent a vertically spanning specimen. Batch 2 had similar specimens with a poor connection at the top, which was meant to represent poor construction practices or shrinkage of mortar. So there were 3 specimens connected to the remaining boundaries, well connected, and 1 specimen which was well connected at the base. Introducing you the test matrix. So 1 specimen from each batch was tested first in plane fully until until ultimate conditions were reached and the influence of the poor connection at the top was studied. Out-of-plane dynamic tests were performed on 4 specimens with different boundary conditions, with fully connected boundary condition, top and bottom connected, fully connected with poor top connection, base connected with poor top connection. And 3 specimens were first subjected to in-plane cyclic tests up to intermediate drift levels, followed by out-of-plane dynamic tests up to collapse, and the influence of the level of previous damage on the out-of-plane behavior was explored. These are the boundary conditions. So you can see at the top, the infills are fully connected to the boundaries, and at the bottom left is the gaps provided at the columns. And you can see in the last picture how we created the poor connection by running a thin saw blade in the mortar while it was still fresh and also after it was hardened. The surrounding frame was fabricated with steel sections filled with high-strength concrete with reinforcement, and it was designed to represent a frame in an existing frame structure and also to remain elastic and so that they can be reused. The frame was rigidly connected to the shaking table with the steel foundation beam, and frame out-of-plane movements were restrained at the top nodes with 4 steel bracings, 2 on each side. In addition to the main tests, material characterization tests were also conducted to determine important parameters of important material properties of units, mortar and the masonry. And also dynamic characterization tests were performed to determine the dynamic characteristics, namely the natural period and the damping ratio of the infill specimens. The in-plane load was applied with a servo-hydraulic actuator in displacement control, and incremental target drifts were applied with 3 full cycles per drift level. The specimens T1 and T6 were subjected to drifts until the ultimate conditions were reached, and specimens T2, T3 and T7 were subjected to intermediate drift levels. For dynamic shaking table tests, acceleration signals were derived from target response spectrum and applied with incremental peak flow accelerations, and the specimens were tested up to collapse. In-plane displacements were obtained using potentiometers, and also out-of-plane accelerations and displacements were measured. Now I will present some main important experimental results, starting from the in-plane response. Force displacement response was obtained, and the specimen fully connected to the boundaries reached an effective drift of 0.87%, and the in-plane damage was characterized by diagonal cracking along mortar joints and also a shear sliding along bed joints. And in this specimen, the shear sliding occurred around 1/3 of the height. And the specimen, poorly connected at the top, reached an effective drift of 1.3%, with similar cracking patterns, but with horizontal crack around mid-height of the panel. And also it had slower damage progression with less damage at the same effective drift compared to the specimen which was connected fully to the frame. And then, according to the damage observed, drift values for damage limit states were derived for both batches. For operational limit state, damage limitation limit state, life safety limit state, and near collapse limit state. And slightly higher values were obtained for infill with poor top connection, which indicates that not having a proper connection can be beneficial for the in-plane response in terms of the drift capacity. Moving on to the out-of-plane results. First, let's consider the specimens without any in-plane damage. The boundary conditions heavily influence the collapse mechanisms and the out-of-plane capacity in terms of the recorded accelerations on the panel, and also the peak flow acceleration at collapse. The specimen which was fully connected had the highest capacity, followed by the specimen which was poorly connected at the top, and then the specimen, the one-way spanning specimen, and the least capacity was observed for the specimen which was only connected at the base. This is the collapse of the infill that was connected in all boundaries, and the collapse featured two-way arching mechanism with trapezoidal cracking and progressive failure of the wedges starting from the top one. For the infills that were previously damaged, the out-of-plane damage progressed from the existing in-plane cracks, and the level of in-plane damage influenced the out-of-plane capacity. The out-of-plane capacity reduced with the higher in-plane damage, and also it reduced further when there was the poor connection at the top. This is the failure of the specimen which had previous in-plane damage of 0.54 drift, and as you can see, the existing in-plane damage led to a loss of masonry in the mid-courses, which led to a horizontal fracture in the upper courses and eventually collapse. Comparing all the specimens, we can say that different boundary conditions and presence of the in-plane damage led to different failure mechanisms. For the fully connected specimen, as expected, there was a two-way arching mechanism with trapezoidal wedge failure. And also for the top and bottom connected specimen, one-way arching was expected with the horizontal cracking along the length at the mid-height. The specimen poorly connected at the top showed a classic triangular wedge failure, and the specimen connected at the base with the poor connection at the top lost its connection at the top very quickly after loading, and it showed a cantilever behavior. And also the infills that were previously damaged, the out-of-plane damage propagated from the existing in-plane cracks, which led to a loss of connection at the top boundary and collapse of the upper portion. The displacement profiles, deformed shapes, were also affected from boundary conditions. Specimens in batch 1 had maximum displacements at the center, and the specimens in batch 2 had maximum displacements at the top. This was also observed for the infills damaged, previously damaged, and with increasing damage, the displacements increased, and also with the poor connection at the top, the displacements were exaggerated. So here, the absolute maximum displacements observed for the specimens with applied peak flow accelerations are compared. The influence of the implant damage is clearly seen here, where the flexibility of the infill is increased with the increasing implant damage, and also having gaps at the boundaries resulted in higher displacements, with the highest displacement observed for the cantilever response. Here I'm showing the absolute maximum accelerations recorded at each accelerometer along the height, and similar to displacements, the maximum acceleration for batch 1 was also observed at the center, and for batch 2 it was observed in the top half at 3/4 height, where the accelerometer was. And looking at acceleration profiles, at the instant of maximum acceleration recorded on the panel, the profiles were consistent with observed deformed shapes, mainly when two opposite boundaries were effectively connected. The acceleration profile between those boundaries were nearly triangular. For example, in T4 in both directions, and in T5 in vertical direction, and in T8 sometimes in the horizontal direction. And this was also observed for the specimens previously damaged. And interestingly, for T3 and T7, which had the most implant damage, the acceleration at the top half was higher than the lower half, and it's interesting to note that the highest damage was concentrated in the upper half of the infill. And then acceleration and displacement hysteresis was obtained for the specimens. And from this, force displacement relationships were derived by considering the acceleration distribution over the panel and tributary masses. And then graphical envelopes were constructed considering the overall maximum these accelerations and forces. And these graphs have been obtained for all the specimens. And here the graphical envelopes are compared for batch 1 and batch 2. The influence of the previous implant damage on the out-of-plane response is clear here, where the out-of-plane capacity and also the stiffness is reduced with increasing implant damage. And also having gaps at the columns led to a slightly different behavior from the other specimens. And finally, the relationship of the out-of-plane peak force, the out-of-plane capacity, with the in-plane drift are presented. So on your left, the reduction factors are presented with respect to the specimen that is well connected, fully connected to the boundaries, where you can appreciate the out-of-plane capacity reduction due to the previous implant damage and also due to the weak top connection and the gaps at the columns. And on your right, the force reduction factor is derived with respect to the undamaged specimen of each batch. And these relationships are important to assess the reduction of the out-of-plane capacity associated with expected in-plane drift demand and also in-plane damage limit states. For example, in the new draft of second generation Eurocode 8, a factor of 0.2 is proposed between damage limitation limit state and the ultimate limit state. And this relationship is somewhat conservative compared to our results. But we should keep in mind that these proposals are based on previous static tests, out-of-plane static tests, which can be conservative compared to dynamic testing. Now I will present the numerical investigations conducted. The models aim to study the out-of-plane behavior without any in-plane damage. And one-way and two-way arching mechanisms were studied using finite element and distinct element approaches. Starting with the finite element model, a macro modeling approach was employed to simulate one-way spanning infill. The model was developed using the Seismostruct software, and in elastic frame elements with distributed plasticity was used with solid square sections. First, the one-way arching with rigid boundaries was explored and compared with theoretical predictions for one-way arching mechanism, assuming uniform stress distribution in the compressed hinges, and also a lever arm of 0.9 times the thickness. A masonry parabolic material model was used, and the sensitivity of the results to a number of elements, integration points, and fibers in the section were these parameters were calibrated, and the material parameters for the material model were obtained from the characterization tests, except for the descending branch parameter, which control the post-peak behavior of the material. So the descending branch parameter, the main challenge in this model was to calibrate the descending branch parameter, number of elements, and the integration points and their interaction. So to simulate the one-way spanning specimen from the tests, the frame deformability was accounted by using zero-length linear spring elements applied at the top of the infills, between the top of the infill and the support. And the spring stiffness was calibrated with a model of the bare frame using SAP 2000. And the numerical results were compared with the force displacement response of the experiment. Interestingly, using a triangular load shape improved the agreement with experimental results, and if you recall, the acceleration profiles were also nearly triangular. In contrast to the finite element model, the distinct element model employed a micro-modeling approach, which represents the masonry as an assembly of discrete bodies interacting through interfaces. And this model was developed with 3DEC software. The units were modeled as rigid blocks with nonlinear joints. And in this model, the frame and infill was explicitly modeled, which allowed to represent any boundary condition. Normal and shear constitutive models were assigned to the joints. To validate the models, we first simulated the small specimen tests, starting with wallet compression tests to calibrate the model's compressive behavior. And then initial shear strength tests, where the shear stiffness and shear fracture energy was calibrated. And flexural tests in vertical and horizontal direction. The elastic and shear moduli were calibrated to account for the stiffness associated with bending. And since in horizontal flexure, both tensile strength in the head joints and also the shear capacity of bed joints are contributing to the flexural capacity, the shear stiffness and shear fracture energy could be recalibrated from the horizontal flexure tests. Moving on to the infills. First, the one-way spanning infill T5 was modeled with nonlinear pushover analysis with uniform loading. The cases of rigid and flexible boundaries with and without geometric nonlinearity was considered. Accounting for the deformability of the boundaries and geometric nonlinearity led to a good match of the numerical results with the experimental force displacement response. And further refining the elastic modulus and also the loading rate led to a better agreement. Similarly, two-way spanning specimen was also modeled. And here, although the out-of-plane force capacity was predicted within a reasonable range, the displacements were highly overestimated. So further analysis are needed to explore two-way arching mechanism with this model. So further improvements that we can consider are accounting for dynamic actions, improve representation of frame and test setup, namely boundary conditions and frame deformability, explore the influence of loading shape, and explicitly accounting for unit, mortar, and plaster. So I will end the presentation with mentioning conclusions and some future work. Accounting for infill typology and boundary conditions is important for the definition of in-plane damage limit states. And out-of-plane collapse mechanisms, acceleration, displacement distribution, and capacity were significantly influenced by boundary conditions. Out-of-plane capacity reduced for increase in in-plane drift demand, highlighting the importance of considering the in-plane out-of-plane interaction in seismic assessment of infills. One-way arching mechanism was well represented in numerical models, as you can expect, but modeling two-way arching was challenging and needs further investigation. Considering frame deformations, geometric nonlinearity, and also the assumptions on stress distribution at hinges were important for the model validation. And some recommendations and future work. Improving current code provisions for defining in-plane damage limit states and assessing out-of-plane capacity and demand is important to account for infill typology, properties, and boundary conditions, and also to consider in-plane and out-of-plane interaction. The numerical models validated in this study can be improved to include in-plane damage and the diatomic response, and they can be used to conduct parametric studies. Subsequent phases of this experimental campaign are already in effect to explore the influence of openings, thickness, and some retrofitting solutions, and some loading protocols, expanding the experimental database. And lastly, the impact of out-of-plane damage on in-plane response and the simultaneous application of in-plane and out-of-plane dynamic action remains an open question. I have come to the end of my presentation. Thank you.
Thank you, Maithree. Exactly 30 minutes. So questions now from the committee. Pablo. Microphone.
Thank you very much for your presentation, Maithree. So, just one question, a comment, more than a question. As you know, of course, most of the experimental tests in literature were performed on scaled specimens and were static tests. On the contrary, you performed a dynamic test on full-scale specimens, which is, of course, the best option because it's the closest to reality, let's say. Okay. Apart from this consideration, if we want to go a little bit more into the details, which specific aspects, in your opinion, you have been able to investigate more accurately thanks to the fact that your tests were full scale and dynamic? I mean, imagine that you have to convince someone that is designing an experimental campaign and to perform dynamic full-scale tests instead of static scaled tests, which are more expensive, of course, but you have to tell him or her, okay, it's better, however, to spend more money because otherwise you will miss these aspects, for example. Okay, which are the most important aspects on this point?
Thank you. At the top of my head, I can think of the arching capacity in the outer plane direction, where the thickness of the infill is important, and where the compressed zone is where the capacity is dependent on the highly dependent on the compressed zone. So maybe this has an influence on full scale and scale specimens, but maybe the relationship between the capacities of full scale and scale specimens can be explored. That can be an interesting question to explore, so we can save some money to explore, to do tests with scale specimens. So that's one aspect that I can think of right now.
Okay, thank you.
First, I would like to congratulate with you because there is also a very huge amount of work in experimental campaign. But I would like to ask you some comments about, firstly, if you, according to your opinion, is possible to, on the basis of your experimental tests, to generalize some out-of-plane behavior that you encounter during your experimental test?
I would say the shape of the observed
according to the boundary conditions.
Yes, exactly. According to the boundary conditions, this can be generalized. It doesn't depend on the accelegrams we applied, for example. Maybe out of play capacity. As I understood the question.
Even talking only about the collapse mechanism.
Yes.
In other words, when you show us that
these are very well-known collapse mechanism for these specific boundary conditions. For example, the two-way arching mechanism, the one-way arching, and also the triangular wedge collapse with the top connection, and also cantilever response. We can expect these behaviors in these tests, and also to observe the collapse mechanisms were more interesting, I think, with previous in-plane damage, where the collapse was mainly the collapse mechanisms were not predictable in those cases. Like it did propagate from the existing in-plane cracks, which can be expected, but in terms of capacity, the peak flow acceleration where it collapses, I think these are important outcomes from this study.
Thank you.
Thank you for the very interesting presentation, and really, I'm also impressed about the experimental campaign, so very extensive. I have a curiosity. You also noticed, of course, the influence of the surrounding frame, of the deformability of the surrounding frame on the behavior of the specimen. So you used steel frames,
Yes.
which are, so how much, of course, and you're thinking about extending the experimental campaign, so I mean, how much are diffused in, and did you evaluate the diffusion of this kind of structural systems, maybe also in different countries? and also the thickness of the infill wall, of course. If you made already some evaluation of which thickness, and of course connected to the weakness of the infill wall in the future could be considered in connection to the type of surrounding frame, what is expected.
With regards to the thickness, this infill typology is commonly used type. It's referred to as weak slender infills, which are used in pre-seismic code era in around 1960s to 80s. And there are a wide variety of infills, as you know, and the frame. I'm sorry, I did not understand the question exactly. So
If there are some countries where steel frames are more diffused,
so this frame was specifically designed for this experimental campaign to be able to reuse them because we had plans for several phases of the experiment. So it was specially designed to represent the deformed shape of an existing reinforced concrete frame structure, which was designed without any seismic code provisions. But you're right, there is a significant influence from the surrounding frame for both in-plane and out-of-plane behaviors. This can be, I think, can be investigated using these numerical models, where you can actually assess how much capacities, how much the influence is from the deformability. You can vary the deformability of the frame in the models and quantify them. Yes. Thanks.
Again, we still have some minutes left, so if there are questions from the audience, Rui.
Maithree, again, congratulations for the work and for the presentation. Just one curiosity, can you tell us a little bit more about the selection of the records that were used in the out-of-plane direction?
Yes.
From the hysteretic results you showed,
Yes.
they seem to have quite a large number of cycles. So I'm curious to what was the thought process
Yes.
to select those records?
These were artificial acceleration records, which were derived from a target response spectrum defined for testing of non-structural elements, which is a bit strong acceleration record. We also considered numerical analysis on frame structures and got flow response spectra and assessed the frequency range where the amplitude was significant. We considered this together with the natural period frequency of the infills, and we calibrated the frequency range and the amplification of this target response spectrum.
Thank you.
Any other question? Well, if not, then we will thank Maithree once again. Thank you. And we leave Maithree behind for a few presentations now and move back to Central South America now with Peru, with Carlos Mesta. Please, Carlos, go ahead.
This is not my presentation. Yeah. I send it by email.
Which one should it be? To me?
To IT support.
So it should be here, I guess, right?
Okay, thank you very much. It's a pleasure to be here. My name is Carlos Mesta, and I will present my thesis focused on modeling and quantifying future multi-hazard risks of cities. I would like to start my presentation saying that this topic is increasingly important as climate change, urbanization, and population growth accelerate. Here you can find some figures that support this statement. For instance, by 2050, it's projected that the global population will reach 9.7 million people. From this population, there is a large percentage that will live in cities, especially in low and middle income countries. At the same time, in the last few years, it has been observed that around 60% of cities globally are exposed to at least one major natural hazard. And lastly, infrastructure and environmental changes continuously reshape vulnerability over time. So an essential risk is dynamic. However, most current risk assessments exhibit some limitations that limit their ability to support decision-making, focusing on reducing future risks. For instance, they relied on past or present conditions of exposure and vulnerability. They underemphasize social vulnerability in contrast with large efforts dedicated to modeling physical vulnerability. Also, they focus mostly on the impact of single hazards instead of considering multiple hazards. They assessed individual assets, mostly buildings, giving less focus to interconnected engineering systems, for instance, and they use incomplete or uninformative risk metrics largely focus on asset losses instead of considering other risk metrics. So in this presentation, in my thesis, the objectives are to model future urban exposure and physical vulnerability to natural hazards, to assess social vulnerability, to model the impact of multiple natural hazards on the built environment, and to investigate comprehensive risk metrics. So I will achieve these objectives by considering several studies that are focused on two areas, in Kathmandu Valley in Nepal and Lima in Peru. In the first part of this presentation, I will talk about urban growth modeling and social vulnerability assessment for Kathmandu Valley in Nepal. Nepal is one of the fastest urbanizing countries in the world, but at the same time is continuously affected by multiple natural hazards. This has been seen in the last few decades, for instance, in 2015 or 2017, where earthquakes and floods affected populations in Nepal. So the objective of this first study is to investigate how urban expansion and social vulnerability could interact with natural hazards in Kathmandu. So as part of the methodology, here I selected existing global models that account for some natural hazards. In particular, I used fluvial flood hazard maps from the FATON global model that accounts for different flooding occurrences associated with 101,000 year mean return period. Also, I selected a global map of liquefaction susceptibility, so the maps are visible in the figure at the right. Then, in the urban growth modeling, that is an important part of the methodology, I employed a cellular automata model that is called SLEOT. SLEOT is the acronym of for the data sets, the data information that the model needs to be run, and accounts for slope, land use, excluded areas, urban extent, transportation, and hillshade. All this information is collected from open data sources. And the core of the model consists of generating growth cycles. So these cycles are controlled by 5 coefficient values that are indicated in the figure. And the combination of these coefficient values are used to simulate different dynamics of urban growth. That could be, for instance, a spontaneous growth that happens in any location in a particular region, diffusive and organic growth that happens around existing urban areas, or road influence growth that account for the importance of transportation network. So there is a calibration stage in the model when we compare the simulated urban maps that this layout produced with historical information with the aim of with finding the best coefficients that better simulate the historical growth observed in past years. So at the end we consider that we could use these coefficients to extend or to simulate future urban growth assuming a business as usual scenario. Then in the social vulnerability assessment, I want to account for the capacity, different capacity of populations to prepare, absorb, adapt, and recover from the effect of multiple natural hazards, because the effects of these events could be disproportionately larger for some population groups. So in the literature, I can find different drivers for this social vulnerability. For instance, the gender, the age, the income, the access to education and health services, among others. And there are many methods existing for assessing the social vulnerability. So here I selected one of the most widely used methods, that is the social vulnerability index. In this method, basically we collect information from census, from national census to represent different indicators or dimensions of social vulnerability, as you can see here in the table. So these variables collected are normalized, are used to estimate different scores per dimension of social vulnerability, and at the end we combine to obtain an overall index. So as part of the results here in the map, you can see results of the urban growth modeling that showed the evolution of built-up areas from the initial year here, that is 2018, until 2050. So according to the model, there is a large increase of built-up areas predicted to occur in the valley until 2050. And also, in terms of social vulnerability, I could obtain a map that could be used to identify the most vulnerable municipalities across Kathmandu Valley, and also identify what are the main drivers of this social vulnerability for each specific municipality. So then, when I cross this information of urban growth and social vulnerability with multiple natural hazards, we could obtain some first screening indicators of how risk could evolve in the next years. So for instance, there is a estimated large increase of built-up areas in regions with the highest levels of social vulnerability. Also, there is a large increase of built-up areas in areas located in the floodplains, as you can see in the figure at the right. And in terms of the liquefaction susceptibility, most of the urbanization is already existing in the areas of the highest levels. So most of future urbanization could be allocated in zones of the lowest levels of liquefaction. So this was part one. And then I will continue with the second part, that is an extension of the part one, that is about the quantification of the potential benefits of implementing risk mitigation strategies to reduce losses in Kathmandu. So I can say that most existing buildings in Nepal are highly vulnerable to floods, to earthquakes, as evidenced in the last years. And this is because several reasons, like for instance, the use of low-quality building materials, deficient construction practices, and poor building code compliance. Yet, the benefits of risk mitigation strategies is still not well understood for Kathmandu. So this is the objective of this second study, to investigate what could be the effects of implementing different plans for reducing financial and human losses in this region. So for the methodology in the hazard modeling, I selected an earthquake scenario similar to the one that occurred in 2015 and affected the Gorkha region. I used empirical ground motion models for simulating ground motion intensities, also accounting for spatial correlation and local site conditions. And then for flood hazard, I used the same data sets than in the first part, that are fluvial-pluvial flood maps associated with two different mean return periods. Then in the exposure and vulnerability modeling, I propose to assess different urban scenarios that represent potential trajectories that the valley could experience in the next year in terms of population, number of buildings, and the prevalence of different building typologies. So here I combined the results of the first part of the urban growth model with projections on population with census data to characterize the residential buildings in Kathmandu. Here I propose two sets of risk mitigation strategies. The first one are focused on reducing seismic risk and are retrofitting the most vulnerable buildings that are basically unreinforced masonry, and building code enforcement for new buildings. And then the second set of measures is intended to reduce flood risk and consists of elevating the existing buildings in the floodplains and implementing hazard-informed land use planning, so basically restricting new urbanization within the floodplains. For the loss assessment, I selected existing and adequate fragility and vulnerability functions for both the seismic and flood losses. So here you can see a summary of the seismic losses obtained through the analysis. There are 4 scenarios that I propose to measure the impact of the risk mitigation plan. So for instance, in the table you can see that there is a large amount of financial and human losses obtained in the baseline scenario A. And we can see that if no risk mitigation actions are implemented in the future, these losses could greatly increase in the future. However, the implementation of retrofitting and building code enforcement could be used to control or mitigate these potential losses in the present and in the future. Also, something interesting is that when we disaggregate the losses by income level, we observe that low-income populations are those that experience the highest loss radius, and this is basically they live in the most vulnerable buildings in the region. And then moving to the results for the flood losses, I also propose to evaluate 4 different scenarios, 1 in the present and 3 in the future. And you can see the description of the scenarios, but here it's important also to say that the last scenario, scenario D, accounts for the multi-hazard nature of the region. So here we combine both risk mitigation actions designed for reducing earthquakes and flood risk. Again, you can see here a table that summarizes the mean loss metrics for the baseline scenario and the comparison with the other scenarios, also observing a significant increase of losses if no risk mitigation is implemented in the future, and a reduction or at least a control of losses if we implemented a risk mitigation plan. Also, when we disaggregate the losses by income level, we find, I find an opposite result compared to the seismic case, because here are the high-income populations, the ones that experience the highest loss radius, and this is because most of these populations live within the floodplains. So this evidence that different multiple hazards could affect different fractions of the population, so risk mitigation actions should be tailored for each specific region and hazard. Then I continue with part 3, that is modeling time-dependent seismic exposure and vulnerability, but these studies focus on a more local scale, a city or a district, in comparison with the region that was the previous part. And the motivation for this third study is that there are persistent challenges in incorporating time dependencies into local scale seismic risk assessments. For instance, urban growth models, as a slide that I showed you in the past parts, are applicable for a regional scale, like Kathmandu. Like their application to a city scale or a district scale is more difficult sometimes because the lack of high resolution data to use these models, but also because at a more localized scale, there are some dynamics that are not well represented in urban growth models. For instance, urban growth models are good for modeling or simulating future expansion, but not very good for simulating urban densification. Also, there are challenges for adapting existing models designed for broader scales, like for instance, the Jane global exposure that provides good estimates at national scales, but when implementing these models to a more local scale, there are some additional considerations to be accounted for. And lastly, there are some local dynamics that should be accounted, like for instance, incremental building expansion, demolitions, replacements. As you can see in the figure at the right, I have an example of incremental building expansion. This is a phenomenon that occurs in a lot of regions around the world, where buildings rarely remain as in the same conditions as originally built. So, for instance, the families or the population living there could add new story, 2 or 3 story in the next decade, so the exposure and also vulnerability changes over time. So the objective of this part is to propose a conceptual framework to better capture these local dynamics for seismic risk. So the methodology is synthesized in this figure. It follows the common structure of any typical catastrophe risk model, consisting of exposure, hazard, and vulnerability model. But here, I propose to include some features that account for time dependencies. For instance, the use of population projections, the inclusion of local dynamics as incremental building construction, demolition, and replacement processes, or the testing of disaster risk reduction strategies. So in this way, we could also track what are the changes of risk metrics over time. So some key features of the methodology are that we intend to model a present and a future exposure using common data sources like, for instance, census data, local data that are important to tailor, for instance, existing mapping schemes from GEN or other institutions that are good at national scale, but need some refinement for local scale. In this case, remote service using Google Street View looks like an interesting option because there are many available data around the world to identify changes and features of the buildings. And for future exposure, for instance, here I propose instead of using urban growth models to rely on master plans that are official documents that describe the zones where urban expansion should be allocated, right? And then I also use the local data for calibrating the vertical development dynamics, like for instance using a Markov change model for modeling the incremental building expansion based on a previous work, or use the local data to calibrate what are the rates of demolition and replacements. So I applied this framework to a case study in Lima, Peru, in the Caraballo district, that is one of the fastest growing districts in Lima. I simulate an 8.8 magnitude earthquake scenario during a nighttime. The exposure is developed with the data sources that I mentioned, including some remote service, some field work to validate the data, and the use of vulnerability functions from GEM. So as you can see in the map, you can see the blocks where existing buildings are, but also the blocks that don't have black borders. There are the zones that, according to the regional authorities, new urbanization should be placed. Also, here I showed you the transition matrix that describes the probability of transition between different states of vertical development. And here you can see that building expansion is an important phenomenon to account for. There are higher probabilities of one-story or two-story buildings to transition to buildings with different building heights, so this should be accounted for. Just a small summary of results. I tested 3 scenarios to investigate the effect of considering these local dynamics. I disaggregate the losses based on the location where the losses are in the existing urban areas, in the new urban areas, or the total areas. And you can see that if we include these local dynamics, we can see that still in existing urban areas there is an increase of losses. also by proposing some risk mitigation actions, we can control this increase of losses in both existing or new urban areas. And just to conclude the last part of my thesis, the intention here is going beyond asset losses and casualties, but focusing on other risk metrics. So this is about investigating post-earthquake hospital transportation for casualties using agent-based modeling. And so following an earthquake, the hospital may face a sudden surge of incoming patients who require hospitalization. However, in the literature, there is still a lack of studies focusing on understanding what are the main drivers of the patient transportation. So here the objective was to investigate the influence on infrastructural and socioeconomic factors on the post-earthquake accessibility of hospitals to injured populations. The methodology consists of two modules. The first one is a probabilistic regional multi-severity casualty model to estimate the number and the spatial distribution of casualties in a region. And the second one is an agent-based model of human behavior to simulate individual and collective actions related to the transportation of patients. Here, I selected a hospital accessibility metric to measure risk. That is the ratio of patients successfully transported to hospital. I applied this framework in a study area, again in Lima, Peru. Here I have two neighbor districts. One is a low income and the other is a high income district. And you can see here that there is an uneven distribution of hospital facilities, but both share similar populations and number of buildings. Some key features, because I know that I'm out of the time, I think. In the first module, the intention is to classify all the population in different individuals in different health states. So the population, depending on the building damage, could be classified from non-injured to severity 1, 2, 3, or fatalities. And here I focus particularly on the transportation of severity 2 and severity 3 patients that are those that require hospitalization with some level of urgency. And the second module is the construction of the agent-based model. Here we represent some actions that have been observed in past events. For instance, the people could arrive at hospital using private cars or ambulances depending on the severity of the injuries. For instance, severity 2 patients could go to hospital if there is some non-injured populations at home and they have a car, of course, while in other conditions, severity 2 or in all the cases, severity 3 patients will need to call for an ambulance to be transported to hospital. Also, there are additional considerations that are described in the slide, like the roads are assumed to be fully functional after the event, and the hospital have coordinated response efforts so they could share ambulance resources to patient transportation. So here, this is a part of the results. These are cumulative arrival curves for the severity 2 patients that showed the evolution of the ratio of severity 2 patients transported to hospital. If you look at the initial part of the curves, you can see that there is distinct proportion of these patients that arrive at hospital in the initial hour. And this is because the impact of the household car ownership. So high-income populations have more advantages and benefits for arriving at hospitals at time compared with low-income populations, for instance. While for the other part of the curve, the ambulances are critical for transporting the remaining patients. Also, this is the cumulative arrival curves for severity 3 patients. Here we see identical trend for both districts, and this is because the assumptions that I consider that hospitals share their resources, so differences in hospital infrastructure or emergency resources do not influence healthcare accessibility. And I also tested alternative scenario to see the impact of, for instance, cooperative neighborhood level response, so neighbors could share their private cars to help other people in the same blocks, or what could happen if hospitals don't share the resources and act independently in each district jurisdiction, or what happens if we double the size of ambulances. So these alternative scenarios and other could be explored with this model. So just to conclude my presentation, this dissertation has addressed the following objectives. The first one was achieved with part 1 and 2 when I developed a urban growth model and combined the outcomes of this model with population projections and other considerations to generate future inventories of buildings and populations. Also in part 3, I proposed a conceptual framework to be applied to a more local scale. And then the second objective was achieved by developing a context-specific composite index to assess the social vulnerability and compare different populations. The third one was achieved by evaluating potential losses from earthquakes and floods in Kathmandu under different scenarios. And the last one was achieved by exploring alternative metrics beyond asset losses to also consider a more broad understanding of risk. So this is all from my side. Thank you very much for your attention.
Thank you, Carlos. So let's start with the questions by the examining committee. Maria.
Okay, thank you very much. This was a very interesting presentation, a lot of results and interesting, also inspiring for all of us who work on these kind of topics. I have two questions. Just first one maybe is more trivial, but just a curiosity about this Sloit model. This for urban expansion, it depends on several parameters that of course are applicable everywhere. So probably it is trivial, but I'm just curious to understand if this model is applied, of course, in developing countries, shows an expansion, but probably in other countries like Italy or where the expansion is probably not so, it should show probably almost constant. I don't know, this is just a curiosity. But then more on the other type of model, more local, let's say, for the referring to the incremental building construction. Of course, in order to calibrate this model, you mentioned also you need more refined data. Which kind of data did you look for, and how accessible? So, which are the challenges to find this kind of data? If it is reproducible, if you think it is applicable in different parts, or it very much depends on what is available and what are the barriers? Thanks.
Okay, thank you for your great questions. So the first one about the slot model, there is a common structure of the model that consists of using different coefficients that could take different values from 0 to 100, let's say. So the model could be applied in any geographical context, but at the end, what we look for is the proper combination of these coefficients that better replicate the data that we collected. So the combination of this coefficient is like the DNA of the specific city. So for instance, in one country, or in some cities, we could find that the diffusion, for example, coefficient is a high value, so it recreates or it simulates or represents a context where there is a lot of spontaneous growth happening in the city, maybe for less developed or less consolidated cities, while maybe for other, there are another coefficients that take a higher value. So this is intended to represent that maybe the urban expansion occur not in a spontaneous growth, but maybe around existing urban areas. So the structure is common, but the combination of coefficients could vary depending on the geographical context. And for the second question about incremental building expansion, I think that the model that I propose here, of course, depends on the availability of data from Google Street View, for instance. And I think that there are many regions where this framework could be applied, because many cities have available data for different years. For instance, in Peru, we have data for 2013, 2023, so a difference of 10 years, but also it's updated continuously. So I think that it's possible to use this framework and be applied in other geographical contexts. But of course, there may be some regions where also the data is available for one specific year. So maybe fieldwork could be applied to complement this data and obtain or track the changes that we are interested in for. So I think that it largely depends on each specific context.
Thanks.
Thank you for your presentation. Just one very quick question. Can we go back to slide number 22, please? Okay, thank you. When we move regarding financial losses, and when we assume scenario D instead of B, so building code enforcement and not only retrofitting, decrease in losses is smaller. Why?
It's a small, you say, right?
Sorry?
Could you repeat the decrease of losses is?
Is smaller.
Oh, yeah.
Yes.
So
it is better not to enforce the building code from the financial losses point of view?
Yeah, I
is
think.
There something?
Yeah, thank you for your question. I think here the decrease is smaller because we're also considering the increase on replacement value of the buildings. So if you look at the loss ratio, the decrease of losses is actually higher, but in absolute terms is not too visible because the differences in the new replacement value of the building stock. So,
Okay. So it comes from some matter regarding the replacement value?
Yes.
Oh, okay. Thank you.
He stole my question. And so firstly, congratulations for the presentation. I would like only to have, in a few words, if possible, from you, to have a brief synthesis of all the methodology you applied in order to be possible to apply it in an unknown location. Could you?
So you mean the applicability of the methods? Yeah. I think that in general, most of the frameworks that I showed here are possible to be applied in different contexts. But of course, we heavily relied on the availability of data. So for instance, regarding to the question of the first examiner, maybe, for instance, if we are interested in assessing local risk for some regions in the world, we won't be able to collect only data from remote service, but maybe we combine with other data sources like information from municipalities or field boards, so they could be added as an additional data source. But the frameworks by themselves, I think that are applicable to the regions. For instance, moving to the last part of the agent-based model for transporting patients, there I represented basically the role of private cars and ambulances, but it's easy to include new agents that, for instance, could represent the actions of police stations or fire trucks. So, of course, there may be some new rules to be added, but I think that the general framework by itself is possible to be used in other contexts.
Any question from the audience? Rui, any question?
Yes. Yeah, I always find these presentations very interesting, so it's easy to have questions. And regarding the last part, the final part of your work, your agent-based modeling of access to hospitals, one of your assumptions, which I believe is a very critical assumption, is that hospitals are accessible, are suitable, are operational. So my question, as well as roads, so my question is, how realistic is that assumption? Do you have data that shows that that is a realistic assumption or not?
Thank you for this great question. Yes, for the roads, for instance, we assume that they remain fully functional because of some characteristics of the building stock. most of the buildings there are low-rise buildings. So according to some literature, the debris from low-story buildings is not assumed to cause, for instance, the close of roads, and also the collapse rate of buildings here, it was very, very low. So also that could support why we consider that roads remained fully functional. Also is because of the large quantities of roads in the city. So it's possible that maybe well, there are different pathways that private cars or ambulances could follow. But of course, maybe if we evaluate a stronger earthquake or an event that produces a higher collapse rate, this could be something to be included. Also, another reason is that for modeling debris accumulation on the roads, we need some high resolution data, the specific characteristics of each building, and this data was not available in this specific case. And regarding the hospitals, here we did not evaluate the post-earthquake functionality of hospital. We assume that, we don't neglect that they could suffer some damage, but we assume that, for instance, the regional authorities, according to the policies in Peru, they could allocate also additional spaces in the case of some damaged buildings, for instance. But again, I think that this is something that could be included to have stronger results.
Thank you.
If there is any other question, we still have time. Well, if not, let's thank Carlos once again.
Yeah.
And this concludes the first set of 3 doctoral discussions this morning. So the examining committee will now meet briefly. They will be back in a few minutes, let's say at most 20, 30 minutes. So if you want to stay around to hear the outcome for the 3 candidates, we'll be happy to wait with you. Otherwise, we will resume at 2 p.m. with the remaining 4 candidates.
before reading the classical formula in this situation, I would like my colleagues of the Commission to congratulate with you for the hard work and good presentations, and we would like also to wish you all the best for the future. Sorry, I need my glasses. By virtue of the authority vested in me, taking into account the successful examination, I have the pleasure to award the PhD Understanding and Managing Extremes Curriculum Earthquake Engineering and Earth Engineering Seismology to Pablo Garcia De Quevedo, don't be angry with me, Maithree Kurukulasuriya, and Carlos Augusto Mesta Cornetero. Congratulations and the best future for you and for your also family that perhaps are there. Congratulations.
So welcome back to those that have attended the morning session, and welcome to those that have just joined us. We are ready to start with a few minutes of delay. As I've mentioned before the morning session, so welcome to this 9th edition of the Nigel Priestley International Seminar. Just out of curiosity, it's the seminar number 23 of the ROSE program, so 23 years since we've been organizing this seminar and listening to the PhD discussions of so many students. So welcome to the students, to the PhD candidates, welcome to their families and their friends. I hope this day will be concluded in the best way possible for yourselves, to conclude a path of 4 years of research, of hard work. And to evaluate that research of yours, we have an examining committee of 4 professors, so Professor Flavia De Luca and Professor Raffaele De Risi, who came all the way from Bristol to attend this session, and Professor Marco Broccardo from Trento, and Paolo Zimmaro from Calabria. So quite a diverse panel of experts. So let's start. We'll start continuing our trip around the world, now to Colombia with Carlos Grajales. Please, Carlos, the floor is yours.
Good afternoon. My name is Carlos Garcias Ortiz, and I will be presenting a study on the seismic risk assessment of industrial facilities under the supervision of Professors Paolo Bazzurro, Dimitris Bambatsikos, and Dr. Vasilios Melisianos. Let me start by defining NATEC events as technological accidents triggered by natural events. Now, if we take a look at the number of NATEC events in the last 70 years, we can see in the image that geophysical NATECs, which are mostly earthquakes, are not very common compared to other types of NATEC. But on the other side, they have proven to be more severe compared to other NATECs, as you can see in terms of human losses and economic losses. This is actually a very famous case. It's a crude oil refinery in Izmir, Turkey, and it was hit by the 1999 Kocaeli earthquake. As you can see, a lot of components got damaged. Several tanks caught fire. It took several days to extinguish that fire. It's estimated that the refinery was out of service for about 1 year. So you can imagine that it caused a lot of economic losses due to downtime and also repair or replacement of components, but also it caused impact to the environment and to the human health. Now, this is not something new, so methodologies have been proposed in the past, but there is always room for improvement. This is because with time, we get a better understanding of the earthquake phenomena. We also get more computational power, and also we get more data. In particular, what are the gaps that we're trying to fill? Missing models for some components, for example, industrial furnaces, and for the piping systems, there are not a lot of models. Then, site-specific vulnerability. We're trying to make a site a hazard-consistent study. So this is important because there are not really guidelines for such analysis in the literature. Then, correlation in seismic response. And this is important because usually there are no isolated assets in such facilities. So they belong to a system. And several damages at the same time may lead to severe consequences. Finally, correlation between seismic damage and material release. The way we get physical effects such as fire, we saw earlier, or explosion is because of released material. So we need to find a way to link seismic damage with material release. Now, what are the objectives? The first one is the development of simplified numerical models for systems of systems. And also, the idea is to consider structural interactions between those components, and I will discuss that into a detail later. Then the formulation of a hazard-consistent fragility assessment methodology. Then we combine to get the risk assessment methodology that we will then integrate with quantitative risk assessment to evaluate possible domino effect, so propagation of damage because of fire, because of explosion. And finally, the idea is to demonstrate the methodology with a case study, and that will be a crude oil refinery unit in Greece. This is the outline of the work. I will start with, we will first go through the exposure modeling, then move to fragility assessment, risk assessment, and the extension. For the exposure modeling, this section is heavily based on this publication. At the end, I will leave again the QR code in case you're interested. Now, this is the case study. As you can see, it's a crude oil refinery unit. It's actually a hydro desulfurization unit. It has 4 large tanks. Tank 1, 2, and 3 are the same model because they have the same substance density. Tank 4 is slightly different because it's a bit more dense. And inside the unit, we have several pumps, heat exchangers, separator, reactors, furnace, a stripper. Also, the piping system connected all of the assets. And as you can see, the heat exchangers are nested in a building. What is the idea? Simplified models, because simplified model is the way for a scalable and practical assessment. Single model per asset. This is important because that way we can track individual failures and its consequences. So we can see the repairable cost of each asset, and also we can quantify how many days that specific asset is going to be out of service. For the tanks, we built 3 models per tank typology with different fill ratios. And the idea of the structural interactions is to track nested equipment, for example, the heat exchangers that are located in the building, but also the interaction of piping with the assets. In the piping model, the assets are modeled as single masses that are attached to springs. The masses and springs represent the components, and the piping segments are connected, all of them. And also special attention is paid to the fittings. As you can see, this is, for example, the model of the furnace. On the left-hand side, we can find the industrial building with the nested heat exchangers. And in terms of numerical modeling, these heat exchangers are subjected to the floor acceleration of the building, and that way we can get the peak component acceleration. And on the right-hand side, we can see the piping model. As you can see, each asset is represented by a dot, and the segments of the piping are represented with lines. Now, let's move to fragility. Also, this is based on this paper that, if you're interested, I will share it at the end. Now, the first step is to do seismic hazard analysis. We went for probabilistic, and the site is Elefsina, Greece. It's a rock site. The 2013 European seismic hazard model is implemented with the ground motion prediction equation from Boran Atkinson, and most importantly, a single scalar intensity measure is adopted. That is the geomean of spectral accelerations between 0.1 and 1 seconds. This range represents industrial components, but also average SA is a good compromise between ease to use and accuracy. It has been shown to be a better predictor of response compared to peak ground acceleration for a collection of components, but also it is easier to implement compared to vector IMs. Now, the idea is to do multiple stripe analysis. What is that? We select a number of stripes, then for each stripe, we select a number of records, and that way we do the analysis. In the case study, it's 11 stripes, it's 40 records per stripe, and each stripe has a unique set of records, and those are selected using the conditional spectrum method. The same set of ground motion is applied to all of the components because there are uniform soil conditions. As you can see on the left-hand side, that is the hazard curve with the stripes. On the right-hand side, you can see for the IM level for a 475-year return period, you can see the target spectrum, and you can see how it compares to the spectrum that we get from the selected records, and the way we build that target spectrum is by analyzing the contribution of all of the scenarios, that's distance and magnitude couples, for that return period, in this case 475 years. Now we check for hazard consistency. This is important because it has been demonstrated by researchers that an unbiased risk assessment needs to guarantee that it is consistent with the hazard of the site. We compare that by comparing the hazard curves from PSHA with the curves that we can get from the selected records. And we did that for average SA, also for spectral acceleration at 0.1 and 1 second. And as you can see from the figure, there is a good agreement between the curves. Let's move to damage states. In this case, the engineering demand parameters thresholds are random variables. They are not deterministic values. And this is, for example, the damage states for liquid storage tanks. As you can see, we have sloshing damage, base plate damage, elephant foot buckling, and we have the threshold and the corresponding ADP. This case is particular because those damage states can be simultaneous. They are not mutually exclusive. So actually, you can get a tank with sloshing damage and elephant foot buckling at the same time. We do the same, obviously, for all the components. We define a set of damage states, and then we run the analysis, and we can get these results. As you can see, these are all the ADPs, so sloshing wave height, base plate rotation, and meridional stress, and you can see the stripes that we have selected in the y-axis. Now, in this case, for example, we have two tanks typologies, and this is for the 90% fill ratio, but we do the same for all of the components. And using those results, we can build fragility functions that we usually do by fitting a log normal model, but this case was also particular because, as you can see from the dotted line, the log normal fit is not a really good one compared to the empirical data that we have from the results. So instead, we went for an empirical CDF fit, only for that case. In the case of base plate, the elephant foot buckling and sloshing damage, the log normal fit is quite good. We obviously do the same for all of the assets and get all the fragilities. And now, this is a demonstration for the unit. As you can see, we selected 4 IM levels corresponding to a 50% probability of exceedance in 50 years, 10%, to 5%, and 2%. Each figure corresponds to this IM level, and as you can see, with increasing IM level, we get more and more damage components. For example, you can see that for the second IM level, we start getting damage of pumps, heat exchangers, but also one of the tanks. And this is important because damage to tanks may result in a very important economic loss, not only because of repair or replacement, but because of downtime. It takes a lot of time to repair tanks, as we will see later on. Let's move to risk assessment. Now, the loss metrics of interest that I am going to talk about is economic losses, and that's due to repair or replacement of components, but also to business interruption. As we mentioned, for example, the Izmir refinery was out of business for 1 whole year, and that's important. For now, no cascading effects, more on that later, and 2 different approaches. The so-called fragility-based, that is the standard approach with fragility functions, and record-based approach. Both approaches include site-specific vulnerability, so they are consistent with the hazard, and Monte Carlo simulation is employed to account for variabilities. For example, as you saw earlier, the EDP thresholds are variable. Now, let's go step by step for each one of the approaches. The first one, the standard approach, the first one is to develop the exposure model. Second one is to get the structural models. Third one is to select IM. The fourth one will be to perform the seismic hazard analysis. The fifth one will be to select the stripes and to select the records. The sixth one to run multiple stripe analysis. We saw this earlier. The next one will be to get the fragility functions, and then for each IM level, we would evaluate damage probabilities reading fragility functions and get loss distributions for each asset. And then we would propagate from asset to system. Finally, we would combine information from the hazard curves with these losses in terms of assets and system to obtain the risk estimates. Now, the record-based approach, which was originally discussed by Karaferis et al., has the same first 6 steps, so we don't need to do really additional things. Instead, we would go record by record in each IM level. So instead of going IM level by IM level, we go record by record. Now, for each record, we would evaluate damage, and we can do that easily because we know what is the EDP value of each ground motion for each damage state of each asset, and we can compare that to a capacity to see if we got violation of that particular damage state. Then we would propagate to system, and then we would combine with hazard curve to obtain the risk estimates. So no more steps, more bookkeeping, because we need to keep track of all the individual results. Why are we proposing the record-based approach? Because at a time, if we have an area, let's say an homogeneous area, and an earthquake arrives, all of the components are subjected to the same ground motion, not only the same IM level. So for example, if we have 2 tanks in the same area with the same characteristics, so same geometry, same field ratio, same substance, if one ground motion is particularly demanding for one of the tanks, we also expect that to be demanding for the other tank. What if we assume perfect correlation between damage states of those different tanks? We would say that it's the same steel batch. Are we sure about that? We would say that it's the same level of maintenance. Are we sure about that? Also, it's practical, in the practice of industrial facilities, it is very common to replace whole areas, for example, of tanks, because of maintenance, of routine maintenance. So an area of one of the tanks may be very different compared to the first one. If we assume perfect correlation, we may be biased. So shall we assume no correlation? We know that the response is correlated because they are subject to the same ground motion. What if we do something in between? Do we have the data to measure that? What about correlation across different damage states of the same component? For example, elephant foot buckling and base plate damage. What about similar but not identical components? It can get a bit more difficult, right? Now, let's move to the direct loss estimation. This is, for example, the replacement value of the different assets that we are evaluating. All of the economic values and the times are based on discussion with experts in Greece working with refineries, and they are referring to 2022 costs. And now the link between damage and loss is through these loss ratios. You see that they are specific for each asset, and they depend on each damage state. So obviously, if we get more damage, we would expect a higher loss. So that's why you can see that the loss ratio for different damage states is a bit different. Let's move to business interruption. This is actually a representation of the network of the unit. As you can see, there are some components that they work partially in parallel. There are some components that they are in parallel, for example, the pumps. That means that if one of the pumps is out of service, the other one can handle the whole flow. In the case, for example, of reactors, they work partially in parallel. That means that each one can handle up to 50% of the flow, and in some cases, for example, for the furnace, that's H01, if the furnace is out of service, the whole chain is disrupted. How do we measure the actual cost of business interruption? By assigning a value for the daily cost of disruption. We do that by using a distribution instead of a deterministic value, and these are the parameters. In our case, it's a log normal distribution. Now, we know how much one day of business interruption costs. Now we have to see how many days the unit is going to be out of service. We can see that by defining some recovery activities and assigning a duration to those ones. These are, for example, general activities for the unit, and then we also define a set of activities for each asset and also for each damage state. And as you can see, we also make the distinction between tanks without replacement, so repair, and tanks with replacement. The activities are slightly different, and obviously also the duration is slightly different. And as you can see, for base plate damage, we can get up to 450 days of business interruption for that tank. That's a lot of money, so that's important. Let's move to the unit risk assessment. I'm going to refer to total loss, so that will be the sum of direct and indirect loss, and the loss metrics will be loss exceedance curves and average annual losses. This is kind of the schema, so 500 simulations for per IM range for the standard approach, 200 per ground motion for the record-based approach, and 4 different conditions are considered. The first one is kind of a realistic condition, it's called the varied field ratios. So tank 1 and 3 have a fixed field ratio of 60% and 90%. Tank 2 and 4 have random field ratios for each simulation. Then condition 2, all times at a 90% field ratio, 60% field ratio for condition 3, and 30% field ratio for condition 4. In terms of correlation, in the record-based approach, we assume no correlation across DS capacities. And this is because what I discussed earlier about the same steel batch. And for the Ferriti-based approach, we have 2 different schemas. No correlation or perfect correlation for identical assets. Now, these are the curves. It's something interesting to see is in the case of the 30% field ratio, we see a very significant drop in losses. That means that when we remove the tanks, the vulnerability of tanks of the picture, the curves change a lot. That's why you can see the big drop compared to the other graphs. And now, let's take a look at some numbers. This is actually the estimated loss for different return periods and for the different schemas that I already discussed. Now, if we take a look at the different operational conditions, only with the record-based approach, we can see that we get very different numbers. That means that if we assume, for example, that all of the tanks are at a 90% field ratio, we may be overestimating losses. It's true that we can consider different operational conditions and make different estimates, but if we only consider the 90% field ratio as representative, we may be overestimated. Same thing with the 30% field ratio, we may be underestimating the losses compared to kind of a realistic operational condition. Now, if we take a look at the difference between the different approaches, if we take a look in the case of varied field ratio, we don't have a lot of differences, but we can see some differences. But if we go to the 90% field ratio, we can see that the differences are a bit more significant. This is because if we consider full correlation, we are overcounting the number of times that all of the tanks are undamaged, but also we are overcounting the number of times that all of the tanks are damaged. That's why you can see that the losses for the 90% field ratio are lower in the lower term period and higher in the higher term periods. But something interesting to note is in terms of average annual losses, we are not bracketing the kind of realistic condition. That means that the average annual loss for the record-based approach at the 90% field ratio is still higher compared to the no correlation or full correlation cases. Let's move to the extension for cascading effects. Now, this is how the approaches are modified. Instead of considering only the, let's say, initial damage state, we consider the final damage state after possible propagation, and then we consider also the final damage state of the system after possible damage propagation, both in the standard approach and in the record-based approach. What is the cascading effect evaluation? An initial event could lead to damage. Then this damage could lead to release of material. This release of material, if the material is damaged, could lead to explosion, could lead to fire. And such release could initiate a chain reaction. The fire from this tank may damage this tank, that may damage this tank, and this is actually what happened in the Izmit refinery. Now, how do we associate damage state to material release? This is how, for example, we do for base plate damage. We can see that each branch of this event tree is a degree of material release. And then, given material release, we can give a weight for the different possible physical consequences, fire, explosion. Then we need to model the physical effect. That means that we need to find a model to estimate the intensity of heat radiation or air pressure at the location of different assets. And then we would compare that to, for example, some thresholds to see if the component in that location is damaged or not. We can go fancier and say that we use probability functions that are probabilistic, but they are not widely available, and they are not available for all of the components. So that's why in the practice we use safety distances. The cascading effect evaluation looks like this. Level 0 is the components damaged by the earthquake. Level 1 will be the components damaged because of the components in level 0. Level 2 is the components damaged because of components in level 1, and so on, until we finish the analysis. That means no more damage or all of the assets are damaged. This is an example. An earthquake hits an area with 3 tanks. Tank A gets elephant foot buckling. Tank C gets base plate damage. We have a major material release from tank A. We have pool fire. That pool fire damages tank B. Tank B is completely damaged because of that heat radiation. It has a catastrophic material release, explosion. That explosion affects tank C, gets damaged, and the chain stops. Now, let me conclude by saying that simplified asset-specific numerical models is the way for a high-resolution risk assessment, because we can track individual failures, but at the same time, we can capture structural interactions. Now, fragility functions are not the only way of performing fragility assessment. We can go record by record, and we can capture the seismic wave correlation. We don't need to do any more steps if we are going with a site-specific vulnerability characterization. We just need to keep track of more numbers, all of the records that we are analyzing. But we are not really doing anything extra. Obviously, in the standard approach, we can get the fragilities from the literature, so we can skip the analysis, but it's not really a high resolution and a high fidelity risk assessment. Then we saw that the decisions on the operational condition of a unit can affect the loss estimates, and also the decision on correlation between assets. Then we saw that seismic damage and material release can be associated by exploiting empirical data, and in the case study, special attention should be paid to tanks. As we saw, damage to tanks may be very important in terms of downtime of the unit, but also pumps, heat exchangers, and the separator, because they may not lead to a very long downtime, but a single failure may disrupt the whole chain, and that's important. The contributions from this work are the numerical models for the piping system, furnace, and the building with the nested heat exchangers, a hazard-consistent fragility assessment methodology for the industrial facilities, also a seismic risk assessment methodology with 2 different approaches, detailed activities for restoring capacity for all of the assets. I only show for the tanks, but we did the same for all of the assets, for the unit, and also the relationships between earthquake-induced damage and material release for the tanks. Future works, a full demonstration with cascading effects, also evaluating the impact of retrofitting strategies. For example, we saw that in the literature, there are some models with very big tanks with isolation that may be a very interesting approach for reducing the vulnerability of such facilities, also including human loss and possibly even human health loss in the estimation, and applying the methodology not for a single unit, but for an entire crude oil refinery. These are the references, and if you're interested in the work, you can find more details in these publications. Thank you.
Thank you, Carlos, for the perfect timing. So let's start now with the questions from the examining committee. Flavia.
Thank you, Carlos. It was a great presentation, and thanks for the work. I have a number of questions, most of them on the aspects of exposure. You started your presentation saying that we have more data. Do you think that in this very aspect of seismic risk assessment in industrial facilities, we can say that we have more data today? Indeed, in the general risk for residential building and so on, I can confidently say, yes, indeed, we are in 2025 and we have more data. Do you think we have more data for these specific strategic facilities?
I think so. I think that fortunately we don't get a lot of these accidents, so that's something that is very important. But for example, this kind of inventory associating baseplate damage with different degrees of material release, we use data from, actually, it's a database of tank damages. It was until 2018, I think, and with that data we were able to kind of make the link between damage and different degrees of material release. So that way we kind of were able to close a bit the gap, because usually what we do is, if we get base plate damage, let's say that we get directly this level of material release, but we are not really certain about that. So for sure, if we have more data, we can get a better resolution, but it's true that there's not a lot of these accidents, so there are not as much as data as we could use to get these kind of relationships for different assets. For example, for pumps, for heat exchangers. The tanks, they are quite studied, so we get a bit more data. But it's true that sometimes it's difficult to get, also because, unfortunately, let's say that the industry is not very open to sharing this kind of data. They don't want people saying that they are not very safe. So that's something to take into account, but it's true. Thank you.
Okay, thanks. Another aspect that I wanted to discuss is about the assumption on the simplified model. You developed a simplified model, and this is indeed the approach that is normally used for risk assessment of this kind of facilities. If we were to evaluate how simplified is, how accurate are these simplified models, and what is the level of generalization that you can have from one plant to another? Basically, you had a case study, you did a lot of expert elicitation for that case study, so you had a good level of information for that industrial facility. How is it possible to generalize? Is the simplified model accurate enough? How we could assess this?
That's a very good question. Actually, there are some researches, mostly in Rome, that they have been comparing results from very detailed numerical models with simplified ones. And they have observed that in a lot of the cases, they match closely enough. Obviously, as you said, if we want to go for the higher resolution and the higher fidelity, we need the very complex numerical models that, unfortunately, with the computational power that we have these days, we cannot afford for a scalable methodology. But it's true that, for example, there are some studies that they have complex numerical models, but they analyze a unit as a whole. So they don't go asset by asset, but they say this is the numerical model of the crude oil refinery unit, and this is the fragility for that unit. So that way we can bypass kind of the asset by asset complex model, but we lose a bit of resolution because we don't know really what's happening with each asset, but we see that let's say the whole refinery is associated to this level of damage, this level of repair cost, this level of downtime. So it's kind of a give and take.
Okay, thank you very much. One last aspect. In this presentation, you didn't discuss much about the code, the regulatory framework around all of these. how prescriptive is the regulatory framework for assessment of risk of industry facilities? And the follow-on question on this is, the manager of an asset of an industry facility, for example, if they do a very detailed risk assessment, do they get rewarded of this more detailed risk assessment in any way if, for example, they find out through a very detailed framework that their risk is higher with respect to... So I would like to understand from the perspective of the impact and the use of this methodology, are managers rewarded if they apply a more sophisticated approach?
So, in the European Union, there is the Seveso guideline. Actually, now we have the third iteration. It's the Seveso 3. In theory, it's compulsory to make this detailed risk assessment of industrial facilities, but there are a lot of kind of blanks. They don't really tell you the level of detail that you have to go. So it's true that probably a manager would not get into the trouble of producing numerical models, of getting hazard consistent variety functions, only to comply with the code, because the code, I don't believe it rewards managers for a higher fidelity risk assessment. I think that the biggest reward is that with more knowledge, they can make better decisions, and they, in the long term, can save a lot of money. If they make more, let's say, smarter decisions, but at the same time, it's true that it's difficult to regulate this kind of facilities because we don't have a lot of data. They are not willing to share a lot of data. There are a lot of stakeholders. There are a lot of people in the background that they don't want to invest a lot of money doing this kind of research. But it's true that, unfortunately, but at the same time, a bit locally, when something happens, for example, the Kocaeli earthquake in Turkey, and we see that we are vulnerable to such kind of accidents, we kind of realize that it's something important, and we kind of push, probably from the academia mostly, change. And I believe that if we can lead the way for a more high resolution, for a higher fidelity risk assessment methodology, and to kind of integrate that in the regulation, that would be the best.
Do you think there is a role for insurance and reassurance to push for innovation in the field, or do you think there is the need of more enforcing code?
I think the role of insurer and reinsurers is very important, because at the end of the day, they are the ones who take the big loss if obviously the facilities are insured. For example, in the case of the Kocaeli earthquake, it's estimated that 95% of the loss was absorbed by the insurer, and that's a lot of loss. So I think that being a key player in kind of the whole ecosystem, they should pay attention to this, and they should kind of push for better assessments.
Thank you very much.
Thank you.
Thank you so much for the very nice and compelling presentation. Disclaimer, I'm a geotechnical engineer. So my question is, you're using a simplified model for structures, and I think it's very modular, so you can easily add soil, which is going to be, I think, a big player in this kind of analysis in terms of soil-structure interaction issues, but also the response of the overall system. So I was wondering whether you guys did perform analysis where SSI comes into play and how that changes, because I believe it may change even, the intensity measure that is going to become optimal in the analysis and things like that. So I was wondering whether you looked at that.
No, absolutely. I think that it's a step ahead that we have to do. Obviously, if we could include site response analysis, that would be better. Actually, there are some researchers in Greece that are kind of using this record-based approach without the assumption of uniform soil conditions. So they are changing a bit the ground motion for each asset depending on the location to account for different soil conditions. So this is a step ahead for sure. This is something that will take some time because it's not very easy to include in such frameworks. But I believe that it's something that we should point to in the near future, absolutely.
Definitely. I have one more question, which is actually kind of a follow-up on what you were saying. It's more of a comment, actually. I've seen a lot of similarity with seismic risk analysis to distributed infrastructure systems. I've been working a lot on river protection levees, and we've been analyzing, not just me, but a lot of colleagues around the world, spatial correlation models for demand and capacity. You were talking about this issue, especially for capacity. I think you guys should take a look to what's been done in the arena of distributed infrastructure systems, because I know this is a different animal, but there's a lot of insights from those kind of analysis. And one last question, did you guys use subduction records?
No.
Because that's, your site is in Greece, you have the Hellenic arc, that's going to be long period motions. So I think that along with soil, one thing that will be very compelling, I think, is to look at subduction earthquakes, because they are definitely possible, they are actually probable in that area. And I think it's going to provide insights, because it's going to be different frequency range, which is probably going to be leading to different results.
Absolutely. Thank you.
Thank you so much.
Thank you very much, Carlos. I very much enjoyed your presentation. Actually, I have a long list of questions, so I asked the boss down there to stop me from going too long. We can discuss anyway later. So there are a lot of things that grabs my attention, so I might ask also some clarification here and there. So you have been very picky, and that's fantastic to be very consistent in the hazard side. And then later you show a lot of other pieces of the chain, for example, loss curves, or other one that looks to me that are out of shelf. And so there is any kind of validation to the other, like distribution that you choose, or they're just out of shelf and that's it?
So for the validation, unfortunately, we don't have a lot of data to validate against.
Okay.
So it's kind of our best guess, based on obviously a lot of discussion with experts. So for example, the distribution of the daily cost of internet interruption, it's based on the expert opinion of people working in the field, working with such refineries. But it's true that those numbers we can't really compare to something, because they are very specific, and unfortunately, operators are not very willing to share some data to validate, to calibrate also. So that's why the idea was to kind of show a methodology that can be applied to any kind of refinery or facility, from the unit level even to the refinery level. And the unit was mostly for a demonstration to show how each piece kind of fits in the puzzle. But yeah, absolutely.
Okay. You then choose here EDP, which is not deterministic, but it is probabilistic, right? So I guess you have a joint distribution of the EDP if you want to account for correlation between one and the other one, or the EDP, they are just marginal.
So we didn't use any cross correlation between EDPs. So each EDP has its own distribution. That's
so
something
they
that
are independent.
Can you repeat?
They are
please?
independent.
Exactly. We assume that they are independent. Yes. We didn't include any cross correlation between EDPs.
Okay. Okay. And one thing, maybe I missed. So you define fragility. Let's take the simplified approach. So you developed fragility for component, okay, and then you transfer this one to system level, okay. So did you had a clear idea of some sensitivity with respect to the system reliability of which component or components failure path were dominating the risk?
So, for example, in the case of the damage assessment, the idea was exactly to kind of identify the key components that for different IM levels we should be taking care about. And for example, we saw that tanks at a 90% fill ratio may be one of the weak links in the chain. And that's why I said that it was important, because that weak link could lead to 1 year of business interruption. So if you only get damage to that tank and not the other ones, let's say, and they work partially in parallel, you may be at 50% capacity for 1 whole year, and that's a lot of money. So that's why in this demonstration we try to kind of identify those weak links, and at the end that's why in the conclusions I said that special attention should be paid for tanks, but also, as you can see in the B, for pumps, heat exchangers and separator.
But you don't have like a probabilistic number to say this is the dominant failure path that contribute to most of the system failure.
So we do, but I'm not showing that here, but it's the tanks. The tanks dominate the picture for very much. It's like something like 90%, something like that, because as you can see, the estimated replacement cost of tanks is way higher because they are very big tanks. They are 80-meter tanks for that unit, and also because the time it may take to repair the tank. So tanks dominate the picture for a lot.
Then
last question, Marco.
Okay. I'll pass the do you have any question? That's better.
Okay,
So,
thank you.
very quick question. How did you model sloshing?
So actually, it was a very simplified way to model, because in the model that we implemented, it's not included directly, but it's a function of the convective period of the tank. There is a very simplified equation in the Eurocode that estimates the height of the sloshing wave from the convective period of the component, and that's the number that we get and compare with the freeboard.
So we have exhausted the time available for Carlos. Thank you once again, Carlos.
Thank you, Professor. Thank you.
And now let's continue with the thesis by Kenneth Otárola from Costa Rica. Kenneth, come upstairs. The floor is yours.
Okay, good afternoon everyone. I'm Kenneth, and it's really a pleasure to be here today to present the results, or a summary of results, of these 4 years of research about dynamic physical vulnerability. I have to say it was quite a challenging time, but also super rewarding, because I have the chance to meet so many talented people, and many of them are currently my friends. So I'm super grateful because of that, and also equally grateful to my supervisor, Professor Carmen Galasso and Dr. Roberto Gentili. So let's start. So what is dynamic physical vulnerability? Well, basically, it's time-dependent physical vulnerability. So how the susceptibility to harm evolves in time. So although in my dissertation I explore many drivers of this dynamic physical vulnerability, and this is not by any means an exhaustive list, it's only the topics that I explore for single assets and portfolio of assets, I will focus my presentation through the lens of a topic which I find the most interesting, because it encompasses many of these components all along, which is multi-hazard life cycle consequence assessment. So the idea was, or the motivation was, to extend the life cycle consequence analysis framework to quantify the performance of engineering systems. So let's see this figure over here. So of course, after a hazard event, you can have a certain drop in performance, and from that point, your system will start to recover to still pristine conditions again. But of course, or however, this might not be the case in the multi-hazard context, because you can have two hazard events too close in time, so you will not be able to make some repairs or some recovery actions, as you can see in here. And also the idea was to account for complex interactions between these hazards, and I defined level 1 interactions, which are the interactions through the nature of the hazards or through the causal relationships between them, and level 2 interactions through the consequences of, or the impacts on the physical environment of those hazard events. So of course, several frameworks have been developed for life cycle consequence analysis. However, they lack of a standard comprehensive nomenclature. They neglect complex interactions like the ones I was just mentioning. Some of them are expensive computational recursive formulations. They neglect partial improvements due to recovery actions. And of course, different hazards have their very diverse damage mechanisms, so you need to tackle this somehow. So this is how I outline my presentation. So let's start with the terminology. So how to establish a standard nomenclature to characterize these interactions from a probabilistic modeling perspective. So of course, we can have non-interacting events, so those events that occur simply independently, but then you can have interacting events and you can have concurrent, those that co-occur in time or co-occur or coincide in space and time. You can have successive triggering interactions. You have one hazard event that is triggering another one. Think about an earthquake triggering a landslide, for instance, and you can have successive altering, so those events that change the rate of occurrence of subsequent hazard events. So things about main shock, aftershocks is a good example. And this is what I call level 1 interactions, usually modeled in the hazard model of a typical risk assessment framework. But independently of the interactions of these hazards, you can always have level 2 interactions. So even if two independent hazard events occur very close in time, you can have these level 2 interactions. So you can have exacerbated consequences, and these exacerbated consequences are very likely to be more than the sum of taking the impacts of each hazard event individually. And we can have instantaneous deterioration due to shocks of these hazards, and we can have gradual deterioration, for instance, because of continuous deterioration processes. Think about aging and environment-induced deterioration. And we can go the other way around, of course. We can have recovery processes. And the way I thought to tackle this was through this life cycle consequence type of mindset. So the framework was about expanding the consequence analysis to incorporate these multi-hazard interactions. And the workflow is rather simple. It's just composed of these steps that you can see in here. I will not go in depth right now because I will explain a little bit of them in the subsequent slides. But what I can tell you now is that this discrete time, discrete state Markovian framework. So basically, in lay words, is that the future state of the system only depends on the present and not in the past. So step 1, derive fragility or recovery models by using a consistent consequence scale. So remember, I told you have very different damage mechanisms. So you want to somehow express your performance domain, or you want somehow to transform your performance domain to a new one, which is consistent between the different hazards. And this can be done by different methodologies, or you can use different consistent scales, like for instance, functionality is one of them, like the example you have in here for a bridge. If a bridge is open, if the velocity is reduced, or if the bridge is closed, or you can use you can go directly to consequences. If certain components are causing exactly the same consequences, well, you can somehow match these to develop these consistent consequence scales. When you define that, you can develop the models, always working on that consistent scale, and you can develop scalar state-dependent relationships that, given the probability of exceeding a certain limit state, given an IM and a prior limit state. So remember, the future only depends on the present. So here is where we are applying that. Or we can have vector value, so vector value models. So think about concurrent hazards when you have two events. You have a storm causing rainfall, floods, and strong wind. So you have different intensities there. Or think about only one hazard and you want to use one vector value intensity measure. Think about flood depth and the duration of the flood, for instance. So second step, so deriving the hazard curves of surfaces or non-interacting hazard events, you can use a typical or standard probabilistic hazard analysis. For concurrent hazards, you can use joint multivariate probability distributions. For triggering interactions, you can use trigger conditional probabilities. And for altering interactions, you can use time dependence occurrence models. So think about non-homogeneous +1 processes, or given my training, I can think more advanced, like ITAS model or BAS model even. for earthquakes, in the case of earthquakes. So then you can estimate the so-called transition probabilities. So you can take these two inputs that you generate, put them all together, and I developed this analytical formulation to account for any of the interactions that I discussed in the beginning. And then you can estimate the transition probabilities, and those are represented in here through the arrows. So what are these transition probabilities telling you is the probability of transition from one limit state to another one. And for instance, in here you have the probability of transitioning from limit state 0 to limit state 3, of course. And of course, given a hazard event, you can also have a chance of staying in the same state. But then you can take these transition probabilities and maybe focus here in this recovery trajectory, where you have a gradual deterioration, which is this continued process in here, as well as instantaneous deterioration, this shock type of drops in here, and then you have recovery. Well, you can use these transition probabilities to build a Markov chain for deterioration processes. So in the analytical formulation I developed, we will have two. So one for the gradual process, so this will be non-stationary, non-homogeneous because it varies in time, likely, and one from the instantaneous deterioration. And of course, we can go the other way around. We can move, or we can have the probability from going from higher to lower limit states, and therefore you can assemble again these stochastic transition matrices. And the deterioration ones will be upper triangular because you're moving from lower to higher, and the recovery ones will be lower triangular because you're moving from higher to lower. So what can you do with these Markov chains? Well, if you assume a certain probability mass functions in the beginning, so let's assume your system is in pristine conditions, 100% of probability of being in limit state 0, and if you, for this particular example I'm showing here, you are not accounting for recovery, well, under the assumption of small intervals where you can only have one type of event, meaning you can have one hazard event, which could be non-interacting, or what I call cluster of interacting hazard events, or you can have recovery in that delta t, basically. So you can again, formulate a little again, analytical formulation, and you can use this Markov chain to see how this probability mass function is varying in time because of these hazard events interacting, or cluster of hazard events. And of course, you can see as time passes, you will move from limit state 0, 100%, and in time you will see that you will have 100%, so you're moving from the lowest to the highest in time. If you incorporate here recovery, of course you will achieve a steady state in a certain point, which is a property of a Markov process. So what we can do with these probability mass functions per each, or the probability of being in any limit state. So let's see this one in here. Well, you can combine this with a consequence model. So the consequence model in here is in expected terms, but it could be a probabilistic model. And this one, what it's telling you are the consequences given a certain limit state. And if you combine those through, depending on if you are using expected, you have your model in expected terms, you can combine them through the law of total expectation to obtain consequences. So let's think about the typical downtime, repair costs, and casualties. But the important thing here is that maybe your consistent scale will vary when you are analyzing different consequences. So by repeating for each delta t, the life cycle expected consequences is obtained as the cumulative sum. So the output of the framework for a single or individual system will be a curve like this, so a life cycle cost. In here I'm plotting repair costs normalized by the construction cost, for instance. But what when you have a network, for instance, you have a system of systems, well, you can estimate the joint probability of being in any limit state for your components. So let's imagine you have this bridge network in here, composed of 4 different bridges with only two states, open or closed. So the total joint probabilities you can have in there are 16, corresponding to each scenario of a bridge open or closed. So the probability of all open, 1 closed, 2 open, 3 closed, and all closed. So an important point here that I also suggest in my analytical formulation is that when you are dealing with regional analysis, when you are developing the hazard fields, you need to account for these spatial correlations and cross-IM correlations, of course. So I suggested first develop those hazard fields for these different multi-hazard, and I will talk a little bit more about that later, and then use again this framework from there. And this is still even more computationally efficient than typically plain Monte Carlo simulation, for instance. But of course, you need a network-wide consequence, so you can associate each of these joint probabilities with a certain consequence. So the example in here, if you close these two bridges, you cannot go from point 9 to point 11, and you will need to go all around, meaning that your travel distance will vary, and this could represent, accessibility to hospital, shelter, school, workplaces, and anything you really like to analyze. So you will have the same amount of consequences. So again, you can combine them and obtain this sort of life cycle consequence curves. So I want now to discuss applications in the lens of informing disaster management strategies, starting from individual assets. So life cycle consequence analysis of individual assets, and I have two case studies. One, a bare moment resisting building frame, and another one, a case study to span box girder zip tie bridge using, I modeled those using, state-of-the-art nonlinear modeling procedures, using fiber sections because I want to model the mechanical properties deterioration due to corrosion. And in here, I'm going to show you first how I can develop, for instance, the input. So how I can develop a fragility model for this, and later I will apply the framework to obtain the curve that I showed you before. So in this case, I'm dealing with ground motion sequences and corrosion. So first of all, I assemble a generic set of ground motion sequences. So I'm using cloud-based nonlinear time history analysis. So it's a non-hazard consistent approach. But in here, these sequences are representing, it can represent any type of sequence. So main shock, aftershocks, aftershocks, or a main shock triggering another main shock in another fault. But we are relying to tackle a little bit of the, these different seismological feature effects. We are relying in average spectral acceleration and much more sufficient intensity measure. But any point in here that you can see is a sequence. So when you take one point, you can build and you can assemble the ground motion sequence. And I just add a zero padding because I need my structure to reach steady state in between and after the ground motion sequence for each case. What about corrosion? Well, I'm dealing here, or I dealt here with pitting corrosion. So apart from uniform corrosion, we can have deep pits in the steel rebar, and this occur in the propagation phase. And of course, this will have secondary effects in the mechanical properties, like for instance, in the concrete cover, in the steel rebars, in the buckling capacity, in the cyclic behavior, and these are a kind of deterioration that we account for I account for in the analysis. But the important thing here is that the fragility models that I will develop are conditioned on a certain deterioration parameter. And an example of that deterioration parameter could be the loss of mass of the steel rebar. And this is implicitly dependent on the rate of corrosion. And what I was doing that because I want a single set of fragility models that can be used for any type of environment conditions. So if so this set of fragility models can be used if you are in marine splash conditions and so on and so forth, or other type of condition. But what about the environment itself? Well, if you plot synthetic or empirical data of the rate of corrosion with time, you will see that you have incredibly high variability in the corrosion initiation time. And if you make a cut in here, you will see that your data is distributed more or less like this, which is pretty much a zero-inflated distribution. So I use a hurdle model to model at each point in time, so I can predict probabilistically what is the rate of corrosion at each point in time as time advances for life cycle assessment. So then I run the cloud-based nonlinear time history analysis, and I develop this probabilistic seismic diagram model. And this one is in terms of dissipated hysteretic energy, because that the energy increases monotonically with the ground motion excitation, and is conditioned on the intensity measure of the second ground motion and the engineering demand parameter of a first ground motion. And why is that? Is because we don't have thresholds, damage state thresholds in terms of energy. So we need a certain way of mapping what is the state of damage. So this model is purely like is a statistical purely model, but even though it follows the physics of the problem. So the nice thing of this model is that I can obtain directly the state-dependent fragility median values and the dispersion of the fragility models. So I can directly take these points from where I can plot fragility models, state-dependent fragility models. So what happened with the corrosion? Of course, when corrosion deterioration increases, you will see that your system dissipates less energy, meaning that you have less capacity. And I also fit a collapse generalized logistic model to predict the probability of collapse following the same assumptions and the same physical assumptions. And what happened with this one, with the deterioration parameter? Well, you will see that when corrosion increases, the collapse threshold decreases, and of course the probability of collapse increases. So you can combine total probability theorem, the fragility models you develop here with the probability of collapse, and you can derive models that look like this. So these are the state-dependent models, but something that you can notice is that corrosion effects are more apparent for higher damage states. So this is how the fragility median value varies with the rate of with the deterioration parameter. But remember, I told you that I can merge, or I can use the hardened model to somehow, well, I don't remember if I say it, but you can use the hardened model I developed, and I can combine it with these models in here, and I can transform, so I can now have models that were conditional on this deterioration parameter, and now I will have models that are dependent on time. So this will depend on the environmental conditions, because remember that the rate of corrosion is a function of time. So now you have a state-dependent model that depends on the intensity measure of ground motion 2 and time. Of course, if your initiation time occurs sooner after your building is built, well, you have higher probabilities of exceeding a certain damage state that if your initiation time is much later in the life cycle of the system. So I will not discuss much about the state-dependent vulnerability model because it's a direct propagation of the fragility modeling, but still you can see that as the deterioration parameter corrosion varies, you can have significant differences, and this is how a state-dependent vulnerability model will look. So maybe something interesting here is that if, for instance, your model is conditioned on damage state 1, your model will start at the expected consequence at that level, and this will be true both for every different condition in damage state. So now I will show you what will result of applying the framework, the analytical formulation I showed you in the beginning, but before a disclaimer. So I also developed fragility models for flood, but I didn't advance that methodologically, so I only use state-of-the-art approaches, assembly-based approaches, so I'm not showing any result here. And I perform a probabilistic hazard analysis to develop hazard curves for flood and earthquake. So we have a building subjected to flood, ground motion sequences, and corrosion, and if we apply the framework, the analytical formulation, of course I don't need to come to say to you here that if you have two hazard events, maybe you will have higher consequences, which is what you are seeing here. But also you can have an exacerbated consequences due to gradual. But maybe a more interesting way of using this framework is for disaster management, to evaluate disaster management strategies. So think about retrofitting this building. So you retrofit the columns, for instance, and you can see that even if you invest a certain cost in 10 years, from a life cycle perspective, well, your actual intervention will be, or your consequences will be much lower. So you invest a little bit more in here, but the total consequences at the end will be much, much lower. So I repeat this analysis also for the bridge, same set of hazards, so ground motion sequences, flood, and corrosion. And of course, we observe a similar behavior. If you include deterioration, you will have higher consequences. If you upgrade the bridge, let's say you retrofit the columns, you will have lower consequences. But the important part in here is that, for instance, in here I'm expressing the consequences in terms of well-being loss. So you can really use any consequence metric, not just the typical ones. So in here you are assessing how the change in travel times really could affect a user in this case. So now for the second application, so for informing disaster management strategies through multi-hazard resilience analysis. So in one of the papers that currently are in preparation, I have this workflow for a decision support system on optimal set of disaster management strategies. But then I advanced a little bit on resilience analysis, and what I have done was to narrow a little bit our analytical formulation, and now I have what-if scenarios of perf or hazards. So I am analyzing much smaller time scaling here. But this will allow me to model this recovery trajectory with much better detail, so I will have a much higher fidelity in my model. So I can actually model the full recovery trajectory, and I can take into account more stochastic variables, like for instance, idle times between, before recovery starts, or the occurrence of other hazards in between and so on. But always you will have level 1 and level 2 interactions in this case. So, of course, you need to start, sitting with the stakeholders, discussing what strategies you want to implement, and then you model the exposure. So for this case study I have in here, I have a virtual testbed which is with characteristics of a typical global south city, and in which I developed like a little road network, bridge network to perform this little analysis in here, or this little illustrative application. So remember I told you before that maybe it's better to produce first the hazard fields, where I co-develop a way of producing multi-hazard stochastic event sets, accounting for the level 1 interactions, from where eventually you can develop these hazard fields, spatial cross-section correlated hazard fields as you see fit. And then you can do the multi-hazard modeling, and this is the case study. I was dealing with flood and earthquake. And in terms of impact modeling, well, I was taking a systemic approach to measure the impact. So first, you will have impact in the physical or the natural environment, and then through fragility functionality models, you can estimate the social or the social economic consequences from where you can extract risk or resilience metrics. And the analytical formulation I develop in here also count directly if you want to account for socioeconomic or demographic characteristics as well. So for instance, if you want to assess a strategy and you want to assess how this strategy benefit a low-income community, low-income population, well, you can set this in this analytical formulation, new one I developed for this illustrative application. So in specific, I wanted to model the impact for a single bridge, what was the traffic flow capacity reduction, and for a bridge network what was the hospital accessibility from the west side of this testbed in here. So how can you move from here to the hospital, which is in the east part of it. So in here we can see just some bridge parametric recovery curves. So for different hazards and for different intensities and for different, for instance, idle times and for different recovery times as well. So you can see they widely vary, but we can actually model this trajectory for these scenarios we were proposing before. So if we set, let's say, 5 strategies, let's say seismic retrofitting, flood retrofitting, reduce idle times, reduce restoration times, and a combination of implementation strategy 2 and 3. And I can give you more details later about this. Well, you can take these curves and you can put all of them all together and estimate a smooth curve. And this smooth curve will have a different shape depending on the distribution you assume to model the occurrence of your second hazard event. So for instance, this is assuming uniformly distributed in a certain investigation time, and this assuming exponential distribution in the same investigation time. But more importantly, you can assess these different strategies. So if you don't have a strategy, what's going on with the resilience, and if you have a certain strategy, well, maybe the resilience will be reduced. So you then can use the system of a system analytical formulation, and you can derive rich network probabilistic recovery curves, as the one in here, from where you can derive the resilience. And then you can run a little decision-making support algorithm. So for instance, in here, you can see that we have 3 criteria: the performance, and you can think of a drop of performance, initial drop of performance, or really any. You can have resilience, and you can have the cost, and you can have thresholds set for the stakeholders. And after running this, and you can choose whatever algorithm you may need. Well, something I observed in this particular application was that strategy 2 associated to retrofitting floods was the best strategy. So some conclusions general, but I can develop a little bit. So the obvious, dynamic vulnerability modeling is essential for multi-hazard risk and resilience assessment. And my framework advanced the integration of multi-hazard interactions into risk and resilience framework, so both through the nature and through the impacts of those hazards, they enhance the understanding of sudden and gradual deterioration and recovery processes as well. So all these different processes that, you have ground motion sequences, you have co-occurring hazard events, or you can have successive events of any type, and the different recovery processes that you may have. And it provides a scalable and computationally efficient framework for risk resilience assessment. And of course, it supports informed and resilience-focused decision-making for critical infrastructure. And why is that? I think this analytical formulation developed is quite practical, because for individual systems, it runs in 1 second, literally. And for a system of systems, it's quite fast as well, and is always faster than plain Monte Carlo simulation. So just an extra, so I don't have time to discuss this, but I also explored many other things. So an interesting topic was earthquake-induced ground motion duration, but this is a work I did pretty much in the beginning of my PhD journey, but I just want to mention in here that also exists. So remember, I told you can use a vector value of intensity measures for a single hazard. Well, this is a way for doing it for ground motion duration and a certain, and another intensity measure, amplitude intensity measure. So some reference in there as well. So thank you very much, and I will take any questions you may have.
Thank you, Kenneth, for also sticking to the available time. Okay, moving on to the questions by the committee. We can start with Raffaele.
Thank you, Kenneth, for this impressive amount of work in this presentation. I have just a few curiosity mainly. So in dynamic risk assessment, of course, vulnerability, hazard, and exposure, they are all time dependent in the short term and long term. Just to make an example, exposure, if there is an earthquake in a tsunami prone area, there is an alarm, some population will evacuate, and therefore you will have less population exposed to the tsunami. And at the same time, you also demonstrated that corrosion is a problem. So if climate change is affecting temperature and humidity, corrosion will be occurring faster, for example, and therefore you will have a more vulnerable model. So what I would like to know is, as a first question, if this model can account for both short-term and long-term on all three components of risk, and if it can account for that kind of correlation between hazard and vulnerability as well, as I was discussing earlier for the case of climate change, corrosion, and seismic vulnerability.
Okay, thank you. So the first is if it can account for the short-term and the long-term changes. So yeah, you put an example of changing in exposure, but yeah, this framework should be flexible enough to take any really assumptions you may need, but I'm trying to think about a short-term example. So yeah, of course, so a short-term will be, for instance, a hazard-reduced event, so it's changing somehow the vulnerability. But something I have not clear from your question is when you say that the population is moving, so are we thinking more about social vulnerability in this case?
Well, you have less casualties, for example.
Okay, so let's casualties in that example. So yeah, but this will depend directly on the consequence model, because an input for this framework is the consequence model you use. And I am not aware of this sort of consequence model, how they vary in time, or having time varying consequence model. But this will come more from that side. And of course, this framework will be automatically, if you change that input, it will automatically account for that. So in the short term, of course, it will do it as well. And in long term, in my opinion, it's easier because you can measure this easily in the long term, right? So like for planning and so on. But I think this will come more from that side, from the consequences part, rather than the specifically the physical vulnerability in this case.
Thank you. Regarding the implementation of mitigation strategies, I can see that there is a flow chart in slide 29, which is very comprehensive. And the very last block was about optimal mitigation strategies. Is there the need for implementing the mitigation strategies back in the methodology so that it's something circular, or is just an output coming out of your framework?
I mean, it's a possibility. So it's always it's an iterative process. So when it's something we call like an agreement, right, between the stakeholders. So if any of your strategies will not reach a certain level of resilience you set in the beginning, well, you can go into the beginning and then change the strategy. So what you want to set is a strategy that at the end will render the outcomes you want. So it's really, really an iterative process. So you can go on the end. You saw that your solution, any of your solutions proposed initially are not the ones you want. So you can go back, define new ones, rerun, and then you can do a little bit of optimization there till you reach what is deficient. Well, for you, what is deficient strategy implementation? And this is the intention since the beginning in the framework.
Because I can imagine the impact of mitigation strategies can be huge. This is why I think this kind of circularity.
Totally agree. But this wasn't the intention since the beginning.
And my last question is about sensitivity. So you have done a fantastic job about considering corrosion and multiple earthquakes. So I was wondering if you have done any kind of sensitivity study to see which one of the two is the most important when it comes to risk assessment.
So I actually ran a random forest to check was the relative importance in between these, which one was more important between the two. And something else observed is that for lower damage states, of course, the ground motion sequences are always more important, but as the damage state increases, you will observe that corrosion starts to be more and more important. So I ran this random forest approach to assess the relative importance of these two variables. What was the importance of the intensity measure of the ground motion in one side, and what the importance of the deterioration parameter. As your damage state increases, you will see that almost even the corrosion will equal the importance of the intensity of the ground motion. So it's something I also explored as well.
Thank you very much.
Thanks to you.
I would like just a clarification. I saw at some point you were using hysteretic energy. So did you use hysteretic energy as an engineering demand parameter? Did I understand correctly? I don't know if you discussed this, but I wanted a clarification. In terms of capacity threshold, how did you manage using hysteretic energy as an engineering demand parameters? How you have been dealing with the capacity thresholds in terms of hysteretic energy?
Sorry, because the story was incomplete in there, but this is basically this model I was developing was a summation of two parts. So the first part was a model of where you relate the EDP of the ground motion 1 to the energy dissipated to the ground motion 1, and therefore you can estimate what are statistically what were the damage state thresholds in terms of energy. And then you can fit another model, which is the dissipated energy of the second ground motion, but that can be put in terms of the intensity measure of the second ground motion, and you can sum them, and automatically you can map what were the damage states from a peak-based EDP, like drift or rotation, any, and you can transform that automatically to energy-based damage state thresholds, and we have done that because, well, basically we don't have thresholds, so far as I know. Although I saw nice studies this morning on that aspect.
Thank you. One last clarification. The frame, you mentioned designed according Eurocode date part 3. Was it because it was an existing building, or was a Eurocode date part 1? What?
No, the applications I show you is for new buildings, all of them. So all of new, so the building was a special code frame. So the application you saw, basically it was a new building. So corrosion effects are not, for instance, are not that apparent in terms of shear failures, for instance, that you may expect from pre-code systems. So I was dealing so this framework or these applications were for new buildings, basically, for buildings that will be built in future.
Thank you.
Thank you very much, Kenneth. I very much enjoyed your presentation too, and congratulations for your work as well as the work before. I just have some technical question that for clarification from my side. So at the beginning you have this Markov chain, okay? So Markov process. So you discretize the time, right? Because in principle you can also use a continuous time a Markov chain, right? In that case you have a jump rate matrix instead of the transition matrix. But my question is, when you use this discretized time, you have many time length scale there. You have the time length scale of the hazard, for example, and the time length scale of the recovery, which are very different. So how did you handle this one really technically when you were doing your simulations?
So this is an amazing question, because the time, this delta t time, is an incredibly important parameter for the processes.
Absolutely.
So you need to explore, so think about main shock, aftershock. So I was telling you that in one delta t, I take the cluster of all the interacting hazard events. So you need to study first, so do a previous analysis of what is the time when your rate of corrosion due to, for instance, the main shock, when this altered rate of corrosion will return to the original value, and this will be giving you this delta t, for instance, in that case of the main shock aftershocks, but you need to do this for any type of interactions. So yeah, the answer maybe is that this delta t is not just any delta t, it's a delta t that you need to think of, and you need to set it in that way.
Okay. Thank you very much. And always going along this direction, so when you have then the recovery, then you have jump back, right? So you jump back. And then on your slide 33, I saw some recovery which was smooth, right? So this is, oh, yeah, that, yeah.
33?
33, yes. Yeah, that. So this is, somehow you have this smooth, sometimes transition, no, that goes up. Is because, no, the one on the left, really. Because the one on the left are simulated, right? The left, my left.
Okay. This one?
Yeah, exactly. So if you have like a Markov chain, you suppose your fourth state, then you jump down, and then you jump up, so it's kind of this staircase. So this one comes out because you are adding the layer of the performance, that they're coming out smooth, this recovery.
Yeah, this is one of the reasons, but also because for recovery, I can reduce the time. Since this is a what-if scenario, I can know when at least the initial hazard event occurs. So remember, it's what-if for two hazard events in this case. So I know when the first occurs. So it occurs at 0. Then I know the first drop will occur in there. Then I will have idle time, and you can use a matrix that will not change your system, will stay, and that's why you see flat here. And then you can use a recovery transition matrix all along there. And then based on an occurrence model, you can model when the next hazard event occurs, and then you use a single deterioration matrix at that point. So it's not really because of the performance, it's because of how this particular problem was set, which is more, a small problem of two scenarios, two hazard events.
Okay, but at the beginning you show 3 or 4 states, right?
Yeah, because this one is a little bit a variation of the initial one.
Okay.
So in the initial one, I am putting everything together using the small interval assumption, but in this one, I am going more in detail at each step.
Yes.
To do this what-if scenario.
Very good. Last question, then I promise you. And just my curiosity, how did you fit state-dependent fragility? So which tools did you use?
State-dependent fragility?
Yeah, you have, for example, the probability of jumping in a state conditional to the EM and conditional to the current state. So,
yeah. So the main, in that case, the main tool that I use is these two models in here. So the first one is this probabilistic seismic demand model, where you can directly, since you are doing this in terms of energy, you can, so it's cumulative. So it will always increase. So you can directly extract what was the previous state.
Okay,
of the
so you
system.
have a continuous measure, which is the energy. When this one passes a threshold, then
Exactly.
that's okay.
So because it is cumulative, so
Yeah,
it's
because
automatic.
the monotonically increase.
Exactly.
Thank you.
Just one comment, which is more food for thoughts, I think in general for the community. This is a great modular framework, so I think that can be definitely used in the future for multi-hazard analysis. This calls for some components that are currently missing, especially in geotechnical engineering, one of which is regional liquefaction models. We'll be talking about it later. There's a need for those kind of models, and then after we establish those kind of models, soil structure interaction with liquefied models will need to come into play, because I was thinking about Los Angeles, for example. There are entire neighborhoods where the fragility, the vulnerability is going to be changing dramatically when liquefaction happens. Then that's not the end of the process. Soil after liquefaction changes its stiffness, it goes up. And so there can be some counterintuitive conclusions coming from applying these kind of frameworks to those cases. So just a comment about that.
Yeah, no, but I totally agree with you. There is a lot of work to do in this field, and I am super happy because every day I saw new developments which are amazing, and I say, oh wow, this is something I should have explored, and so on. But yeah, totally agree with you. Thank you.
Okay, we actually still have 2 minutes, so if there is any question from the audience, we can take it.
If there's no audience, I will play the role of the audience.
No. One question. Do you want?
Yes, if there are no question from the audience.
No, I don't think so.
Okay.
Go ahead, just
So
one.
it's very quick. So when you did the multi-hazard, then you consider combining two Poisson processes, right? So they are completely independent, right?
No.
No. Okay, good.
So
Can
you mean when I
understand?
developed the stochastic, multi-hazard stochastic
Yes.
event sets? So no, they are, well, is a competing Poisson process, this particularly way I was proposing here, but you use basically homogeneous or non-homogeneous Poisson processes. It depends on your interaction. But I also co-developed a way of transforming the non-homogeneous process to equivalent homogeneous one, so you can directly.
Yes, okay, that I agree, but you have a Poisson process for hazard 1 and Poisson process for hazard 2, right?
Yes.
And those are independent.
It depends on the interaction. So if they are interacting, they are not independent.
Yes.
They might be independent, but for instance, if you have a triggering interaction, they will not be.
The triggering,
Yep.
okay.
So, or the altering, any of them will not be independent. So, for instance, if you see this case in here, I was plotting the case of altering interaction. Yeah, maybe it's not so visible in here, but you can see that you have a main shock in here, which is blue, and then you have an aftershock rate of occurrence, which is this like sort of triangular one. So this one depends on the main shock, and then you will have one that it will decrease in time.
It's more a causal relationship.
Yep, it's a causal. Yeah, so we can, through this approach, we can model this causal relationship through a Poisson competing process.
Very well. Thank you once again, Kenneth.
Thank you, Professor. Thank you.
So we will stop now for a 30-minute coffee break downstairs, and we will be back here at 4:15 for the last two discussions.
1, 2, test, test. Good afternoon, everyone.
Just to check, I think I will have to lift it, right? No, now you leave it for you.
So we are ready to restart for the final stretch. And the first candidate of this last session is Savvinos Aristeidou. Savvinos, please, from Cyprus. Go ahead, Savvinos, whenever you want.
Good afternoon, everyone. My name is Savvinos, and I'm very excited to present to you on this fine afternoon my PhD thesis titled Advances in the Practical Application of Next Generation Intensity Measures for Efficient Seismic Risk Assessment. This thesis can be thought of being divided into two distinct parts. The first part has to do with ground motion directionality in the inelastic spectral displacements and how it can be applied for the seismic risk assessment of bridges. And the second part has to do with a generalized ground motion model that includes next generation and conventional intensity measures, and also an application to the seismic risk assessment of bridge structures. Ground motions are typically recorded in two orthogonal directions in the horizontal plane, but we combine the intensity measures from the two directions into one scalar IM. Usually the geometric mean is used, and more recently the orientation-independent ground motion intensity measures, horizontal component definitions are used, the ROD-50 and the ROD-100. However, in this manner, we lose information about the directionality of the ground motions, which can be significant. For example, two extreme cases are shown here. On the first panel, it's an extremely directional ground motion with a directionality measure of 1.4. And in the second panel, it's an unpolarized or non-directional ground motion with a directionality measure of around 1, or a directionality ratio. This is the elastic trace response of a single degree of freedom system. However, we decided to study the directionality in the inelastic realm, so from the inelastic spectral displacements point of view. So we extended this elastic directionality measure into the inelastic directionality measure, which can be also considered as a secondary intensity measure, and it can give more information on potentially the structural response directionality. So from a subset of the NGA WES2 database, we defined a single degree of freedom system as a bilinear, non-evolutionary, not degrading system, and the ground motions were rotated from the 0 to 180 degrees with an increment of 6 degrees. The output was the 50th and 100th percentile of the displacement response. And from all the ground motions, in the subset that we chose, the geometric mean of this inelastic directionality measure was calculated and extended from the elastic directionality model of Shahi and Baker 2014. And as we can see, for periods of above 0.3, the higher the inelasticity in the system, the higher the directionality and the directionality measure, and also the standard deviations follow the same trend. While for periods lower than 0.3, we saw that the opposite trend was taking place. Having all this data, we fitted a ground motion model for the SDI ROD-50 and the SDI ROD-100 intensity measures, which can be used to better estimate the inelastic directionality at the site given a set of predictor seismological parameters shown here. So the model was calibrated for each period and for each strength ratio. The model performance was checked with the residuals, the inter-event and the total in this case, for the magnitude and distance, in which we saw that there was no apparent bias in the model, and the R square was about 0.8 in most of the cases. And we can see that also the homoscedasticity assumption of the model can be valid in this case. We compare this model with two different other models from the literature that estimate the inelastic spectral displacements and take the strength ratio as an input. It was difficult to find other models that predict this IM, but two of the models in the literature were extracted, and we plotted here the rupture distance attenuation plot. And we compare with the cloud mean of the data, which we can see that our model does pretty well in capturing the trends. And the variability of the ground motion model is also plotted, in which we can, for the intra-event standard deviations, the inter and total standard deviations, where we can see that the model keeps pretty reasonably low standard deviations. And it can be also noted that the standard deviations don't change that much with the strength ratio. So from this novel intensity measure, we explore how it can be compared with other common intensity measures used for the risk assessment of bridges, and how ground motion with directionality can bias the bridge's response. As most of us know here, the IM is very important within the performance-based earthquake engineering framework, and the SDI ROD50 was explored as potential and improved IM to estimate the elastic deformation and collapse of bridges. But apart from the IM, also the horizontal component definition is important, so we checked the performance of different horizontal component definitions, the ROD50, ROD100, and geometric mean, to understand where these IMs rank among other conventional IMs used for bridges. And combining also these different horizontal component definitions, we can get information about the directionality, which current seismic design methodologies do not specify the expected degree of directionality of bidirectional ground motion shaking, but bridges can be sensitive to input records with intense directionality effects because they have asymmetric stiffness and damping and strength characteristics among the two different principal directions. So we used a case study bridge that was documented in the literature. It's a highway overpass in California, and we modeled the pier with distributed plasticity with fiber sections, and the abutment with springs connected with rigid links for the longitudinal and transversal and vertical direction, as it can be seen in these plots. From the pushover and moment curvature analysis, we identified the collapse drift of the bridge, actually the pier, which was the only damageable component for the purpose of this comparative study. And from the model analysis of the bridge, it can be seen that it's a pretty regular bridge since from the first 4 modes, it can be seen that the significant modal mass participation ratio is accumulated. 200 unscaled ground motion records from the NGA West 2 database were chosen from an intense scenario, and this was done to avoid very high scale factors, since it was very hard to bring this well-designed bridge into collapse. So we performed an incremental dynamic analysis for each of those intensity measures with 3 different period ranges of average spectral acceleration. Then we check the sufficiency of each intensity measure against magnitude, distance, and scale factor, where we plotted the residuals of each intensity measure versus each of the seismological parameters, and we fitted a linear regression line. And with green are the IMs that perform the best Also, it should be noted that we have two different metrics to assess the sufficiency of each IM, the p-values and the simplified relative sufficiency slopes. And it can be seen that for the first metric, we want a high p-value, and the SDI rho T50 with strength ratio of 3, 4, and 6, they achieve very high p-values compared relative to other IMs. And also, we want a low absolute value of the simplified relative sufficiency slope, which it was seen that the SDI IMs do pretty well, and also the SI 1 second, and the FIV3, and the peak ground displacements. The efficiency of the IMs was also checked for the different, along the ADP range of the bridge response. In the beginning of the inelastic behavior of the bridge, it was the SAT1 that performed the best, then it was average spectral acceleration, and towards the heavy nonlinear stages and towards collapse, it was FIV3 that performed the best. Also, the dispersion of IM given EDP for the different horizontal component definitions is checked for the elastic and for the inelastic IMs, where the rho T50 was seen to perform better than rho T100 for the elastic IMs, and the geometric mean and rho T50 had about very similar dispersion for the elastic case, but for the inelastic IMs, the rho T50 performed better than the geometric mean in most of the cases. Also, it should be noted that the SDI with different strength ratios perform better in the different stages of nonlinear response. In the beginning, it was the strength ratio of 2 that performed the best, then it was strength ratio of 3, and then 4 towards the collapse. And then the bias of the bridge response against directionality was checked with this. In the beginning, it was in the left-hand side. It's about the same check with sufficiency, but now we have the elastic directionality measure and the inelastic one. In the elastic directionality measure, it can be seen that the collapse residuals are not very influenced by it, but they are getting biased from the inelastic directionality measure. So different IMs, they are getting biased by it. And also in the right-hand side, we can see the SAT1 at collapse. And again, we see the same trend. We don't have any trend in the elastic directionality measure, but with the elastic one, we can see negative slopes with higher R square and lower p values, which means that the IMs at collapse, the collapse intensity measures can be partially explained by the higher inelastic directionality ratio. So moving on to the second part of the thesis, given the different comparisons of IMs, we wanted to explore, to answer the question, what is the set of IMs that can give the best overall predictive power over the structural response? And while there was a plethora of ground motion models for spectral acceleration, there were very few options when we wanted to explore next generation IMs. And also correlation models that connect conventional and next generation IMs a few correlation models are still missing from the literature. So the goal became to develop those models and then explore how they can better the risk assessment of bridges. So we used artificial neural networks to develop the generalized ground motion model that included many IMs, since these can capture the interdependencies among the multiple IMs, and we can simultaneously regress all the IMs using a mixed effect regression, and it can provide ease of use for users. Since using different ground motions to predict different IMs that were developed from different ground motion databases, and they use different regression schemes, they can introduce some heterogeneity into the ground motion selection, into the hazard, which can then be propagated into the seismic analysis and risk assessment. So a set of 9 predictor features were used for this model, with the mean and max values shown here from the subset of the database, and the predictor IMs, the response features of the IMs that this generalized ground motion model can estimate are shown here, and the different horizontal component definitions of each IM. And 2 different period ranges were used for average vector acceleration. This is the model architecture, the artificial neural network model architecture of the ground motion model, with one hidden layer of 150 neurons and the response layer with 169 neurons, which is the amount of individual IMs predicted by this model. And this is the functional form of the fixed effects model, which was then fed into the mixed effects regression. And then after we fed the model and we did all the necessary performance checks, we compared with 7 different ground motion models from the literature that predict the similar IMs. 2 of those models are developed with machine learning methods. And these are the comparisons, these are the magnitude amplification plots for spectral acceleration of 1 second, and this is the distance attenuation plots for SAT1, in which we can see that all the different models are very close. But we can see discrepancies, especially in the significant duration, in the FIV3 and the average spectral acceleration, which indicates that these IMs, the scientific community took less care in developing ground motion models for these IMs, and all the attention goes to spectral acceleration, but they can be important as well. This is the residuals checks for inter-event residuals, for intra-event residuals, and for total, in which we can again check that there is no bias from the model and no dependency on the rupture parameters. This is the dispersion of the model for the inter, the intra, and the total standard deviation of all the different IMs that are included in the model, and compare with the standard deviations of the Campbell and Borzognia 2014 model, the peak ground displacement, the 2 definitions of significant duration. This is a machine learning model, also this one, the FIV3, and the only model available for the direct estimation of average spectral acceleration. The Campbell and Borzognia model, by the way, estimates the spectral accelerations. This is the comparison when we use that model to estimate the indirect average spectral acceleration. And we can see that the total standard deviation of the model was low for most of the IMs, especially at longer periods. The next step was to develop correlation models for the different next generation and amplitude and cumulative density measures using artificial neural networks. Since, as I said before, there are very few models available in the literature or even missing, and they are required for the ground motion record selection, for vector-based PSHA, and for the calculation of ground motion fields. These are the different models from the literature that we use for comparison, and the empty cells are the models that still miss that are still missing from the literature, they have to do mostly with the FIV3 and with the direct average expected acceleration with other IMs and with themselves. This is the indirect calculation of the two models that can be used for the indirect calculation of correlation models of expected acceleration to average expected accelerations. So there is still no available model for direct estimation of those correlation coefficients. So this is where this thesis comes to fill this gap with 24 cross-correlation models for the horizontal component definitions listed here for the different IMs, ROT50 and geometric mean. To fit those empirical correlation coefficients, artificial neural networks were used, and an example of the SA to FIV3 correlation model, for example, is given here with two hidden layers, and this is an example of functional form of those artificial neural networks for the case of one hidden layer. This is the correlation coefficients between spectral acceleration, in which it can be seen that the ENN model predicts very close correlation coefficients with the empirical one, and which can be better appreciated also in the slices of those correlation coefficients and the comparison with the different models from the literature. It can be seen that our model has very close correlation coefficients with the Acaredol 2014, and we have also stronger correlation coefficients than the models of Baker and Jayaram 2008 and Baker and Bradley 2017, which is also the case for the duration, where our model predicts stronger negative correlations. This is the correlation between SA and FIV3, in which it was seen that the FIV3 was mostly correlated with spectral accelerations of medium to high periods, which is something expected since it has to do with long period velocity pulses. And it's also weakly negatively correlated with the two definitions of duration. And this is the direct SA to SA average correlation model compared with the two cases of indirect method with the same ground motion model and different correlation models. As it can be seen, even when the same ground motion model is used and different correlation models are used, these correlation coefficients can change. So there is a need to make a unified approach, to come up with a unified approach to have direct correlation coefficients between expected acceleration and average expected acceleration, and because this can influence the conditional spectrum and then the selection and the risk estimates. And this is the correlation of average expected acceleration with duration. In the case of direct correlation of FIV3 with itself, we can see that it's very correlated, taking values of correlation from 0.84 to 1, and it can be seen also in the slices where we compare the correlation models of SA with FIV3, which tells us that this can be treated also as a period-independent IM. And then, having developed all these ground motion models and correlation models, we applied it into the risk assessment of a set of bridge structures to see how much these advanced IMs can improve the risk estimates and the dispersions. So, and we have applied it in 7, and we also checked the influence of the different combinations of conditional and matching intensity measures. So a set of 7 case study bridge structures were used, and they were classified as irregular and regular according to the pier height arrangement along the length of those bridges. they had a rectangular cross-section, and a lamp plasticity was assigned in this case to the piers of the bridges, and also in cycle and cyclic degradation damage. Cyclic and in cycle damage was added into the lamp plasticity models to account for the cumulative effects of the ground motions. The PSHA was carried out for each of the conditioning IM for the case of each structure, and the hazard disaggregation, for example, for F5E3 is shown here, and the different hazard curves. Different ground motion selection schemes were used with varying complexity, ranging from just scaling to SAT1 to conditional spectrum to generalized conditional intensity measure. The case 0 was the case of just scaling to SAT1, which is what we do in incremental dynamic analysis. The case 1 was the conditional spectrum, the case 2 was GCIM, including the different IMs, and the different cases have to do with conditioning or matching with next generation intensity measures. As an example, the case 2, the distribution of the selected ground motions of the case 2 is shown, in which we can see a pretty good match of the GCIM distribution, the theoretical distribution, and the selected ground motion records. The hazard consistency was checked also for each case, and a multiple stripe analysis was carried out for each ground motion record selection scheme and for each bridge structure. And we compare different metrics of these ground motion selection cases. The first one was the intensity-based evaluation, in which we compare the median of the EDP given the IM level or the return period, given no collapse as well, in which the most important information is that the case 0 resulted in low medians because it had lower than expected acceleration spectrum, and it resulted in low EDPs. And for the case of regular bridges, it was the cases of conditioning to F5E3 that resulted in very high medians compared to the rest of the cases. This is the dispersion in the intensity-based evaluation, but it's better looked at from the demand-based point of view, since it's more related to risk estimates. So it can be seen that in the beginning it was the cases conditioned on SA average that performed the best in the first stages of nonlinear response, and then for the irregular bridge, and then for the case and for the heavy nonlinearities and towards collapse, it was the cases conditioned on F5E3 that had the best performance. And it's interesting to note that in the regular bridges, the cases that were conditioned on F5E3 had the best performance in most of the nonlinear range. Also, it should be noted that the cases conditioned on SAT1 resulted in the highest dispersions, and also when the duration was matched, then these dispersions became a bit lower, and it can be seen also in the risk estimates, where the cases that duration was not matched, they resulted in higher risk estimates because those selections had higher durations than what theoretically expected. So they resulted in high risk estimates. And the lowest risk estimates were found in the case 0. And it's interesting to note how the cases 9 and 10, which are considered the best cases in this case, they converged to very similar risk estimations. They result in the same seismic demand hazard curves. So to conclude, the key findings and contributions of this thesis was the development of orientation-independent inelastic spectral displacements, which introduced also the concept of inelastic directionality measure, which is an extension from the elastic one. And as we saw, it can potentially bias the structural response and can give more information than the elastic directionality measure. And also, the SDI-ODNN was proposed as a novel intensity measure showing good performance in estimating the bridge response. And it was showed that the ROT-D50 had offered higher accuracy and efficiency than the ROT-D100 horizontal component definition. And we developed also an artificial neural network-based generalized ground motion model that includes multiple IMs and horizontal component definitions. And it offered low dispersions and high predictive accuracy. Also from that, a total of 24 correlation models, cross-correlation models bridging the conventional and next generation IMs were developed and proposed. And the predictive models was with artificial neural networks, and it enabled the multi-IM ground motion selection and the different comparisons that we saw at the last part of the thesis. It was applied to 7 bridges, and we saw that the GCIM based selection with also matching the duration was the case that outperformed the other approaches in almost all evaluation metrics. Both ground motion models can be found in the OpenQuake engine. The correlation models are planned to be implemented soon, and they are also available in the GitHub online in these links. This is the list of journal articles that were stemmed from this research, and thank you for your attention.
Thank you, Savvinos. So let's move on to the questions by the examining committee. Marco.
Thank you very much, Savvinos, for the great presentation, and thank you also very much to share your report. So I enjoyed to read it and examine it. So I make you some subsample of questions that I had while I was reading your thesis. Some are curiosity, other are more technical notes, but I try to be sure to leave the space to the other. So the first curiosity that I had, it was, there is this empirical evidence that for period lower than 0.3 or for period longer than 0.3 there is a strong polarization, and conversely is not there for 0.3. So that's an empirical observation, but can you build on this observation and give some physical explanation?
Yeah, so because we use the strength ratio here, for shorter periods, it behaves, the single diaphragm system behaves like more like a rigid block that suddenly there is a snap, and so for lower strength, for lower strength ratios, it snaps and it's more, there is more standard deviation in the directionality measure, and that gives also higher geometric means. For higher strength ratios, there is higher nonlinearity, so it's lower standard deviation and lower geometric mean of that inelastic directionality measure. But this should definitely be explored more because we don't have any other observations from before to compare with.
And do you think that because you use correctly a constant strength reduction factor, right? So another approach is maybe more like in line with, we'll say, displacement base, to use more a constant utility demand. So repeat your analysis in this way. So do you have some thoughts about that, and are you expecting actually to then finding a relationship between the two?
Mm-hmm. Yeah, the reason that we used strength ratio was that the single degree of freedom system can be defined directly, while if you have ductility, displacement ductility, it has to have some iterations. And we had already a lot of iterations because of the different orientations that we had to rotate the ground motions. But for high periods, with the equal displacement rule, we can assume that
this is true for long period. For shorter period, it's more equal energy rule, right?
Equal energy rule is for short periods, as I remember.
Okay, so there is some differences there.
Yeah, and that's why, but for engineering use, periods lower than 0.3 seconds, we don't find much use. Usually we use higher periods.
But
so,
depend.
Yeah, but still it was interesting to note this behavior.
Yeah, good. I'm just make another question and I leave the round to the other end and maybe I will close with the final question. So on the second part, when you use the artificial neural network in general, so everybody knows it's a very high parametric model, right? But that's okay. Once in the future we just plug as input and output, and that's fine. My concern is more when you use it for the correlation model, no? Because you have results that they are, I'm saying, too good. What I mean with that? I mean the following. I mean, you see, you cannot even distinguish basically the green from the blue. So at that point, why don't we use just the empirical? There is way less parameters. You just do an interpolation there, and you have probably an order of 10 less parameter to save.
Yeah. So in the correlation models that are available in GitHub for users to use, we have both empirical correlation coefficients fitted with linear interpolation between them, or we provide also the ANN trained model. So essentially it's a way in which users can interpolate those empirical correlation coefficients. The alternative will be to develop functional forms for each correlation pair.
Or use a non-parametric method, in the sense that you just pick up the green one, and that's it. The empirical one, sorry. You pick up the empirical one, which has less parameter than the black one.
Mm-hmm. Yeah, the users can, there is an option in GitHub, and users can use the empirical correlation coefficients instead of the predicted if they don't want. But we gave both options because usually until now correlations were either given as a table or as functional forms. And for some correlation pairs, it was even easier to come up with artificial neural network models because we don't have legacy functional forms from before. So we had to come up with the functional forms and then see if they are fitted.
Yes. My point was if the functional form has more parameter than the empirical data, then just use that. That was just an observation. Yeah. Okay.
Two quick questions. The first one is you have done some efficiency study on intensity measures. Have you done any relative sufficiency study for those? And the second question is, how did you define the hyperparameters of the neural network? Have you done any sensitivity analysis about that?
So the first question, I didn't get it. Sufficiency and efficiency, we did it here. But you mean in the second part of the
I was wondering if you've done a relative sufficiency study of the intensity of the new intensity measure that you were studying.
Of the ones, we just studied the efficiency, which is the dispersion, along the ADP response of these next generation intensity measures, and also the risk estimates, so the seismic demand hazard curves. But we didn't study the sufficiency of each ground motion selection case. Since we had the eventual seismic demand hazard curves that they include most of the information, we didn't do sufficiency checks for this part.
Thank you.
For the hyperparameters in the ground motion model or in the correlation models? Both. In this, we did a cross validation of the ground motion model, and we selected the best model, and we compared also, for example, the coefficient of determination and the MSC, the mean squared error for each IM. So after these checks, and we did many model iterations, and we selected the best model that had the lowest MSE and the highest coefficient of determination. And the hyperparameters were chosen from the cross-validation, essentially, with different tests and training sets. And for the correlation models, we used, for each correlation model, we again changed the different parameters, the epochs, the batch size, the number of neurons, the activation functions, and it was done manually in the cross-correlation models because it was a simpler problem. So, manually and just visually checking that they fit well the empirical data.
I have a couple of questions that pertain to both sections of your thesis. So the first one is, a suggestion. So we've been seeing over and over that the cumulative absolute velocity is a very good intensity measure when it comes to infrastructure systems. So I would suggest to try and explore whether this is the case for these kind of applications as well. The second one is about the ground motion model development. Did you do any regional correction? So your model, in other words, is your model just the global model using the NGOS2 database, or you also have correction factors for specific regions?
So the cumulative absolute velocity we didn't check, we didn't include in the checks because we had FIV3, and we saw that the cumulative absolute velocity is not used that much recently, but still it will be good to include. Regarding the second question, no, it was we didn't have any regional adaptations. It was the NGOS2.
Because since you do all of this beautiful work, now there's, in the literature, there's two schools of thought. One saying we have to have regional models with only data from that region. So a lot of people develop ground motion models in Italy with only Italian data, okay? They have some specific features typical of that region, okay? Second school of thought, which is the one I think it's better, since regional data only have, a limited amount of data points in that region, we expand, because we can't wait for 1,000 years to, increase the data range. So instead of waiting, we enlarge the geographic area. This is the ergodic assumption, okay? If we do that, then we have a global model, which is the global model from NGOS2. That model doesn't have specific peculiar characteristics of each region. For example, Italy, Greece, Japan, Turkey, they have a strong and elastic attenuation with distance which is not present in a global model. For that reason, NGOS2 models, they do include regional corrections. So if you use a global model, a global data set without regional corrections, you don't take full advantage of the reason why you are using a global data set. So I strongly encourage to look at an elastic attenuation beyond 80 kilometers, and there is a rich literature on that. Italy is proven nowadays that has a very strong elastic attenuation. It's a simple correction that I strongly encourage to do. Short advertisement, we just published online the gmdatabase.org, which is a relational database with all NGA East, all NGOS2 data. We're working on NGOS 3, so it's there for everyone to use. It's been released recently. Last question.
Thanks.
When you modeled your bridges, there's some topography there. So my question is, since we usually have bridges where we are crossing irregular topography, did you account for wave passage and topography together in your response model?
No, but we had different bridges with different pier height arrangements.
Right.
But we didn't account for water passage, for scour.
No, not scour. Like seismic waves, you explore directionality. So if there is directionality, they arrive first at the first pier, then there is a delay, then they arrive to the other pier. If you have a irregular topography, there are some shadowing effects going on. So if you don't couple those two problems, you are missing something in the analysis. So my encouragement is, if you didn't do it, it's something that I think will be worthwhile looking at.
Yeah, we applied the asynchronous motion, not asynchronous, to all of the supports, the abutments, and the bridges. But yeah, ideally, it should be asynchronous motion, which is different in each location of the piers and the abutments. But since this is a comparative study to check the different IMs, the difference, of course, it makes a difference globally, but relatively, we wanted to just check the relative.
Definitely. But in the future, you have all these exceptional framework. I think it's easy to plug this in and account for wave passage and topography together, and you guys can shade some light on that specific issue, which is not
Let us
explored.
move to Flavia to see if she has any question. Do you have any question, Flavia?
Just a quick one. Thanks for the work. I had a question about the constant R approach, but you addressed it when Mark asked. The choice of R. So let's make a scenario that you want to use in elastic displacement as intensity measure for a structure. How do you choose the strength reduction factor, and can you use a single strength reduction factor, and does this introduce issues?
It depends on which range of inelastic response of the structure we want to have the best control over. So if we want to have better capture the collapse of the structure, I would go for a strength ratio of 4, 5, 6, and that can better estimate the heavy nonlinearities and the collapse of the structure.
Okay, so your suggestion is not a structure-dependent strength reduction factor, but more a performance-dependent strength reduction factor for your intensity measure.
Yeah, exactly.
I see. Okay, thank you.
Thank you. And thank you, Savvinos, once again. Okay, and we end our journey staying in Europe, in Montenegro, with Lana Todorovic. Actually, Lana and Savvinos deserve an additional share of applause because they've waited the entire day for this moment. So Lana, please, the floor is yours.
Thank you. Good afternoon, everyone, and thank you for attending this presentation in which I will address some challenges that exist with modeling of liquefaction. which is a when soils temporarily behave like liquid, and its impact on the built environment. So the ground failures that arise due to landslides or liquefaction can cause significant threat to built environment and people, yet they are commonly omitted from traditional hazard and risk assessment studies that estimate the range of exceeding a certain decision variable due to ground shaking solely. But before I explain why ground failure matters, I would like to give you a reason why this is typically done, why they are omitted. And one of the reasons is because liquefaction and other triggered perils have been seen as a low contributor to the overall losses in comparison with the ground shaking counterpart. Other reason would be is that we lack comprehensive data sets that would allow us to develop models and to do a broader assessment of impacts that liquefaction or any triggered peril can pose on the built environment. So, given these reasons, does ground failure matters? And the answer is yes, because in the past events we have seen examples of impressive damage to transportation network, to utility network, but also to bridges and buildings that were found on liquefiable soil and otherwise would withstand the shaking. But also this was not something observed in very past events. Also recent examples of damage to the built infrastructure confirm that these ground failures due to liquefaction should not be excluded from risk studies. Then we try to answer with this thesis the following question: can we develop, calibrate and validate models that can be applicable on regional to global scale? And we try to look whether we can have a framework to assess the impacts of these perils in a similar way that we do for ground shaking. So in the first part of the thesis, the goal was to actually develop a model using non-parametric machine learning technologies, given that they are now very applicable to solving geotechnical engineering problems in general. And the goal was to develop a global model. The second objective was to have a closer look at the empirical models for estimating the displacements, rather than focusing on developing yet another model, given that there is limited data at this moment. Then, while there was attention given to assess liquefaction and its impact, relatively low attention was given to actually enable the open source tools to allow these type of analysis, and the goal was within this thesis was also to expand the capabilities of the open source tools, such as OpenQuake, to allow large-scale hazard and risk assessment due to liquefaction. And at the final stage, the goal was to actually implement these models and tools to evaluate the hazard at continental scale and perform event-based risk assessment at the urban scale level. So this is how I organized today's talk. I will first walk you through how we can model liquefaction and the surface manifestation today that can be generated, but also in this stage I will also demonstrate some examples that will focus only on a single scenario. However, what we also care for is to account for the contribution of all events that can cause non-negligible liquefaction effects. So we'll also see how we can use these frameworks to compute on probabilistic assessments. Then once we know that there is the potential to have liquefaction at the site, we need to understand how large and how severe the consequences are. That's why we look at the displacements. And in the end, we are going just to combine all the pieces of information with some additional information on the exposure and vulnerability to understand how we can assess the risk and how much is the risk due to these perils. But before I jump into the model development, just traditionally how we model liquefaction is one of the most preferred approaches are the geotechnical models, the site-specific semi-empirical models that are very good to use in the regions where we have data. But if we want to also consider it on a large scale, then they become cost prohibitive. So we need an alternative that will allow us to do something on a large scale and assess the impact over the extended geologic settings. So what we do is we actually rely on the use of the geospatial models that are cost-effective and scalable procedures, and are very useful in the regions where we have no data or we have very limited data. And our focus is going to be on these tier 1 models. So the goal here was to create a global model that has a global character, and in that sense we gathered information from over 40 events in which liquefaction manifestation was observed. And also, since we wanted to predict locations where it will not happen, we also included some events in which we don't have liquefaction. And as we can see here in this figure, liquefaction is typically presented at various spatial coverage. In some cases we have very nice polygons delineated where liquefaction occurred and where it didn't. So we classify those events or inventories as spatially complete. But in some cases, in other cases, in most of the cases, we will have liquefaction reported at discrete locations, and in that sense we call those events spatially incomplete. And we organized also these data in GIS readable format. So why do we need this classification in spatially complete or incomplete? Because it will help us create a grid of samples where we don't have liquefaction manifestation. And it's quite easy in case of the spatially complete events, because every point that is outside the polygons where liquefaction was observed is classified as non-liquefied. But in case that we have spatially incomplete events, in that case we don't know the true extent of liquefaction usually, so we need to follow a procedure in which we create the buffers along every liquefied point, and in that sense we sample everything that is in between these buffers. Also, to avoid that the one event is dominating the fitting procedure, we selected from each model maximum 1,000 points for each of the classes. And since we don't know the true extent in our database of liquefaction to no liquefaction, we chose the sampling balance, which resulted in the equal sizes of both classes. So now, in the previous step, we prepared our output labels, but we also need to somehow infer the key parameters that are driving the triggering and manifestation potential of liquefaction. And in that sense, we can talk about density. And density is typically inferred from these global data sets, such as the slope-based shear wave velocity, but also a set of parameters that we can develop from digital elevation models. We also need to know about the saturation, and saturation is accounted by considering the water table depth or some climate inputs that are important because surface manifestation tend to be less severe when earthquake occurs in dry seasons. And also we need to characterize the dynamic component or the ground shaking, and in this case we rely on the use of peak intensity measures, so where peak ground velocity correlates better with ground failure problems. In case that peak ground acceleration is used, then it should be corrected by the magnitude scaling factor, because both amplitude and duration matters for the ground failure problems. So we've seen that we have multiple parameters to choose, but what we wanted to check is what is the optimal subset of these parameters that correlate the best with the model problem, and in that sense we use the methodology that is developed for assessing the IMs for the structural analysis problems, but is extendable for the geotechnical earthquake engineering problems. So in that sense, we assessed every possible input parameter, ranked them using the modified dispersion or proficiency, and whenever this metric was low, that indicated a strong correlation with the modeled phenomenon. And of course, we coupled these results with the understanding of the modeled phenomenon, and in that sense, we came up with these 5 inputs. Now that we have the input and output, the next thing we do is we fit the model, and we use the non-parametric machine learning model, and we need to understand the performance of this newly developed model, and whenever possible we compare the results with the existing models. And first we started with just comparing the discriminatory power of the model, and we can see that it shows good performances. But also what we wanted to check is the residuals in the predicted likelihoods. And in that sense, what we did is we actually looked at each event and computed the residuals in which we compared the predicted and empirical probabilities. And we did it on event level basis because we wanted to understand how scalable the results are. Now, looking a bit closer into these residuals, we compared with one of the models that are also having global character. And in that sense, we just wanted to see whether the residuals improved, actually decreased. And we can see that in most of the events it actually reduced. Then another level of application was to grab a real scenario that occurred recently and caused notable shaking in regions where we had susceptible units, but also with high triggering potential. And in this case, what we did, we also compared this model with the event-specific model that was developed for this region, so calibrated only on the data coming from this region, and we expect that this event-specific model is going to have lower false negative rate. However, even that our model is showing higher negative rate, it's actually still good given that it has a global character. And also one disclaimer is that the comparison with the false positive rates was not done because the data, the observations that I use are actually the preliminary attempt to map the liquefaction extension, so it was not done on whether that is a true spatial coverage of this event. Then these models are very simple in nature and can be used in large-scale assessments. However, there are some uncertainties associated to these models, and they're coming from various sources, modeling error, data gaps, or among others. And what we did is actually we propagated these sources of uncertainties into our calculations. And for each grid, for each point in our grid, we can compute what is the mean likelihood, but also the associated variance. And if we are looking at the relative uncertainty, we can see that it tends to be low in the regions with high triggering potential. And this is just an example showing on a real event how we can propagate these uncertainties into our predictions. Now that we see how these models work on a specific scenario, we wanted to see how the spatial distribution of liquefaction potential can look on a large scale, and also assessing the contribution of many earthquakes. So I would like to just explain quickly how it has been typically done in the past, and it was the pseudo-probabilistic or conventional liquefaction hazard analysis was used, which means that the probabilistic seismic hazard analysis due to ground shaking was performed. We choose the return period for which we want to do disaggregation analysis. We depict the scenario, and starting from this selected scenario, it's actually the liquefaction is assessed deterministically. However, there are some issues with this because a misconception that is coming is often assumed is that the return period of liquefaction estimated effect has the same return period as the ground shaking from which we did the disaggregation. And that would hold only if there are no uncertainties around the liquefaction estimates. However, that's not true. The second issue is that using a single scenario, we suppress the information on the recurrence rate of liquefaction. Therefore, we need actually to provide a more holistic representation and account for the contributions of multiple earthquake sources and propagate the uncertainties in the source modeling and ground motion modeling. So in that sense, we can use two approaches, either the classical PSHA, PLHA, in which we capture the information from the full hazard curve due to ground shaking, and also account for all the magnitudes duration effect coming from all contributing magnitudes, or to use the event-based scenario in which we generate a set of ruptures, couple them with ground motion fields and site model, and then for each ground motion field and combination of site model, we compute the liquefaction footprints. And we organized all of these results to compute the spatial distribution of liquefaction on a continental scale in Europe. And given the size of this analysis, what we had to do is actually to filter out some sites for which we assume there will be low susceptibility and also low triggering potential. There is one thing that we also did not consider in this study because it was computationally too heavy, and that's the spatial correlation in the liquefaction manifestation. And these structures have been observed in the past events and should definitely consider when analyzing risk for the spatially distributed systems. So here just depicting the regions where we have higher rates. That's in the regions with moderate to high seismic hazard coupled with susceptibility that was computed for Europe. Now that we have seen how we can do the assessment over a large scale for manifestation, now it's time to see how severe the consequences are. And depending on the terrain's topography, various ground failure can be induced. We can have cracks in flat terrains, on gentle slopes or toward the free face lateral spreading, and also on steeper terrain we can have slope failures. And our goal here will be to assess, have a closer look at empirical models for lateral spreading, given that these can extend over several meters and have detrimental potential as shown in previous earthquakes. So unlike the case for the developing the model that is predicting the possibility of having liquefaction probability, when we want to assess the displacements or develop models for displacement, we deal with a lack of data, and we have very limited amount of data because we need the measurement, but we also need extra information on the topography or site characterization, and these things are not available for all the lateral spreading measurements that happened, that generated. So we collected the data that is available, and then we just showed the distribution to understand in which regions of various seismological, geotechnical, or topography parameters we are missing, we have gaps in data. And we observed that there is uneven distribution within tectonic environments, with a single tectonic environment dominating the data set. Another thing that we noticed is there is a limited records of very large displacements over 6 meters, which indicated that these models cannot perform well for predicting large displacements. But before I talk about the performance of these models, I would like to give you a quick overview on how we can estimate ground shaking at the liquefied site, and there are several methods that are used typically, and each of these methods can lead to very different results that can have further cause inconsistencies in the assessment of triggering or displacements. And here we examine some of them, so considering like conditioning ground motion fields on the seismic station data to understand whether a better definition of the ground shaking is going to give us a better prediction in the ground failure displacements. And this is done on an event that is well recorded in the past. And we do this because the uncertainty in displacements is largely driven by the definition of the seismic demand. And now what is common shared attribute among these models is that they are having predictions that vary between 50 and 200% of the observations. So we wanted to see whether, which model performs the best. And we considered here 2 models, and the only difference among these models is how they define the seismic component. So in one case, it uses the causal parameters of the earthquake, which is magnitude and distance. And in another case, it's using the spectral displacement. So what we did next is we tried to compute the normalized residuals for these displacements and see how their distribution fit the standard normal. But we see that while on the trained data set there is a good agreement when we test these models on the data that came later, we see that there is a very large departure from the standard normal. And also next, what we did for the second model is just grab the displacements that came from a single event, and we try to understand whether the bias is going to be improved by conditioning the shaking data, and it decreased. However, significant uncertainty remained that should be addressed by considering other sources of uncertainty and also maybe developing better models as more data become available. And in the final stage, I will do walk you through the risk assessment studies. And then we chose a region that had actually observed repetitive manifestation of liquefaction within a single earthquake sequence. And also it is a region where we had actually a lot of geotechnical data. So what we wanted here is to see how we can compute risk in a similar sense as ground shaking. And we did that on a portfolio of buildings that were consistent of only reinforced concrete buildings and that were grouped into three heights, low, mid, and high-rise buildings. And for each of these buildings, we assumed that they are going to be founded on shallow, flexible foundations. So what we did first is we looked at how vulnerable these classes are that we considered into our model, and what we've seen is that we actually chose the set of analytically derived fragility curves from literature, combined them with a consequence model to develop probabilistic distribution of loss ratios. And here we can see that the low-rise buildings are the most vulnerable, however, that the high-rise buildings are showing very low vulnerability. But that's only because we focused here on one type of ground failure, which is the lateral spreading, and the high-rise buildings are expected to behave as rigid bodies, which was not considered in this case. Then next, we wanted to understand where our building exposure is located, and we see that most of the buildings are founded on the soft soils, on the gentle slopes, but we also have some buildings that are located over the free face, where we expect that the lateral spreading is going to be more severe. Also, for some characterization of soils, we have here some parameters that are typically derived from the boring samples. However, in case if we don't have them, we need to rely on the statistical relationships that are developed, and typically, in this case, was what we used was the one developed typically for this region. And then we combined all of these information with the goal to compute the risk. And we actually considered several matrices. One of them is the average annual loss. And what we observed is the average annual loss ratios were higher toward the free face of or near the river, which is expected because free face displacements at the free face are larger. Then the next way to communicate loss was to use the loss exceedance curve, in which we computed the total curve, but also disaggregated them by the building classes. And we see that actually the low-rise buildings were the one that most contributing to the loss, given that they are dominating the exposure model, but also are the most vulnerable. On the other hand, the mid-rise buildings were the buildings that actually were least contributing to the losses, given that they were located in the zones of gentle slopes with diminishing effects of the free face ratio. At the beginning, I said that one of the reasons that I chose this region was because there was a lot of geotechnical data that is actually needed for computing probabilistic displacements. However, This is actually rather an exception than a rule in most of the regions at risk, and we don't have this luxury of having an extensive geotechnical investigation. So what should be done is actually explore the use of geostatistics in order to infer the values at the locations where we don't have measurements. However, one should be particularly careful about the minimum required measurements in order to provide reliable interpolation results, especially in complex and heterogeneous terrains. And with this, I would like just to give a quick overview on the conclusions and achievements within these theses. And one of the conclusions is that liquefaction definitely should be assessed through hazard and risk frameworks in a similar way that we do with ground shaking. And other also ground failure displacements should be included, not only the lateral spreading. Also, that geospatial models is actually a good alternative when we want to do assessment in regions where we don't have data or we have very little data, but it's also good when we deal with large-scale assessments. Then what we also did is conducted a hazard and risk assessment on large and urban scale, and with a goal to understand how the liquefaction hazard varies spatially in Europe. And what is also essential is that we actually have the tools to do this analysis, and that all these models are actually available, so everybody can check on more real case scenarios and try to do also an analysis in a probabilistic manner. So this is like a summary of the achievements. Now there are several geospatial models available in the open quake that could be tested. And then there was a contribution to another model for global scales. And we also computed the probabilistic liquefaction hazard map for Europe and demonstrated how to conduct risk assessment due to secondary perils. And some future research, definitely we should work on expanding and getting more data, and to develop scalable computational frameworks. Also, what I didn't consider here is the spatial correlation in manifestation of liquefaction, which is very essential given that to ground failures is actually the spatially distributed infrastructure that is particularly vulnerable. And also in the case we need more vulnerability functions that will cover various building typologies, not only the reinforced concrete buildings. And with that, I would like to thank you for your attention and to answer any possible questions.
Thank you, Lana. 2 minutes before the time limit. Questions from the committee? Pablo?
Thank you, Lana. I think this is a study that goes towards the direction that the whole community needs. You identified a lot of issues, solved all of them. I think that there is a lot to do still, but this is probably where we are heading to when it comes to geospatial models. So I really think that this is one of the improvements we can do as researchers in the future. Couple questions. One is, when you define liquefaction manifestation areas with your models, did you use any clustering models to delineate areas where that manifestation probability is higher? Because that's one of the issues I encountered a few years ago doing similar things, and yeah.
Yeah, I'm aware actually of the model that exists to do that. But I mean, this was done in the early stage of my PhD, so at that moment I didn't consider that, but I'm perfectly aware that exists and should be definitely considered to inform us better where we had manifestation and where not.
Yeah, no, I think that that would be a very nice improvement because otherwise we may have the risk of having many false positives. So that's one of the things that. Yeah, the second one is you ran a lot of scenario-based analysis, I think 100,000 or something.
Yeah.
My question is, did you try to use the same approach, an event-based approach, but with hazard-consistent subset of scenarios using one of the existing models that are out there? Because this is something that I haven't seen. There's models to select subsets, and authors suggest to use them in geospatial analysis, but I haven't seen them applied to these kind of applications, and I think it would be very insightful.
Yeah, I'm aware that it exists, but no, at this stage, no. But I know that there are methodologies to actually select the hazard consistent scenarios, and from there we do this. But no, in this case, I just was considering taking the source model that exists and from there generated multiple ruptures. And
because for you guys, you did all of the work. I think it's going to be low-hanging fruit, and it's going to be very informative. Last thing. You were showing that idea of using kriging, I think,
yes.
to evaluate, when you have CPT data scarce areas. I don't remember if we published these, but in that paper I was alluding to with the clustering algorithm written with Zach Bullock, we also, I think, proposed something like that using geology and or VS30 as proxies to define classes of CPT profiles that then can be analyzed using Monte Carlo simulations, and that I think will be something that should be done. I haven't seen it done yet, but again, you guys did this exceptional work. I think that all of these little extra efforts will be worthwhile, because then the community will gain a lot of insights.
Yeah, that could be actually another level to improve and to have better information on where to use and how many of these inputs to use.
All right, thank you so much.
Thank you.
Thank you very much for this very nice presentation. Just a couple of questions. Can you elaborate a little bit more on how you have created the database of liquefaction, non-liquefaction cases?
Mm-hmm. So yeah, basically what we did is went through all the available reports after the field missions to understand whether there was liquefaction or not. And in some cases, there were examples where actually the polygons were available. And then for each of these, if we have liquefaction at a discrete location, yeah, we use that as a location for our models. But in case when we have these polygons, then we just sampled. We set up a grid, and whenever a point of a grid is falling into, actually I should show it here, falling into this polygon where liquefaction occurred, we classified it as liquefied, in other cases as non-liquefied, but the data is, the information is coming from all the sources in the literature, field mission reports or remote sensing data.
Yeah, this leads to my second and last question. So I totally appreciate that this is very important when you don't have data scarcity is always an issue. So, but for some of these points, you may have the data. And if a stratigraphy is available, have you tried to do some comparison even with, for example, Sid and Idris approach, something very, very simple, some sort of tier 2 approach? So I don't know if there is any comparison. Unfortunately, I didn't have the availability of the thesis, which I would love to read, but I'm just asking now. So your geospatial methodology has been verified for some points with any simple tier 2 assessment.
So basically, these models can be actually coupled and should be tested with geospatial, with geotechnical models. And actually, there was a study in which the comparisons among the geotechnical and geospatial was compared for New Zealand, where there was a lot of data, and they were actually showing like very close predictions. So.
Okay, thank you.
Thank you.
Thank you very much, Lana. I will be very quick this time. For first reason, this is not really my topic. Second, I'm tired too, I guess, like everyone. So I have one curiosity is the following. So your probabilistic model is basically a binary classification 0-1, right?
Yeah.
Either liquefaction or not, with multiple input there. So when you fit this basically logistic model, your data set is balanced, has a lot of 0 and 1s, is kind of balanced or not?
So it is balanced, but there are some, these probabilities that are, because we can also associate to each of the classes the likelihood of having it. And these probabilities, because we have a balance, I didn't know the true extent, these probabilities can actually be biased, and then there are alternatives like there is a way to modify these probabilities in order to unbias them and to account for the extent that exists, and that would be done by fitting a logistic regression in just using the data for which we know the true extent. And that in this sense, that would be the case of New Zealand, where we have where we have mapped polygons and we know exactly where liquefaction occurred and where it did not.
Okay, great. And then I have a curiosity. At slide, I think 23, when you have the European model of liquefaction, I think 22, 23. The next, this one, okay. Then I read up there annual rate of liquefaction occurrence, right? Then I see very, very red into the Pianura Padana, where more or less we are. So it's greater than 10 to the minus 1, so the returning period is about less than 10 years. Now, unfortunately, I have several decades, and I cannot really recall big liquefaction problems here. Am I missing something, or is this somehow validated, this map here?
That is actually a future step, actually, to validate these models, to understand where we can improve. But at this stage, I did not validate them. It will be part of the future.
Okay. Thank you very much.
Thank you.
Super quick, in terms of collection of data, you mentioned water content and seasonal variation.
Yeah.
Which kind of source of data did you manage to find? According to my experience, this is the information with which you struggle more when collecting information. It's hugely important and affecting a lot the results. So I wanted to understand how did you deal with this?
So basically these are just layers that are globally available, and for example the water table depth is not, it's a static, it doesn't account for the fluctuation, but also I use the precipitation data that is coming from, those are historical measurements. But there are also, I've noticed that there are some future predictions that could be actually used for us understanding like how in future liquefaction can change due to these seasonalities.
Thank you.
Thank you.
I don't know if anyone from the audience wants to ask any question. I think everyone is very tired. I'm giving you the opportunity because we are a little bit ahead of time with Lana. So, if not, then this is it. Thank you, Lana, once again.
Thank you very much.
And you know how this goes now, so the evaluation committee will meet and soon they will be back to let us know the result. Stay around.
Congratulations to all of you. We have enjoyed your work. Now I will go ahead with the formal formula. So, by the virtue and authority vested in me, taking into account the successful examination, I have the pleasure to award the PhD, Understanding and Managing Extremes, Curriculum Earthquake Engineering and Engineering Seismology to Savvinos Aristeidou, Carlos Fernando Grajales Ortiz, Kenneth Emilio Otárola Madrigal, Lana Todorovic. Thank you very much. Good luck for the future. You did very well. Congratulations. Well done. Very well done. Congratulations. I hope you enjoyed.